first one is the output SBOM. This just describes the packages, the distributable artifacts, and the metadata. So like that's the kernel and the kernel modules. We have a source SBOM. This describes the used source files with their metadata like license file hashes. And we have the build SBOM, which lives in between and links the sources to the build and explains the intermediate steps. And one weird quirk until now is that we need to distinguish which file is a source file, which file is a build file. And we right now do that by understanding in which directory it lives, if it's in the source directory or the build directory. And so this is a limitation. If it's not an out-of-tree build, we merge the source and the build SBOM into one, since we lose the ability to distinguish between them. But that's also work in progress right now. And in the end, the structure within the files looks like that, which is messy and too small font and not understandable, but I will go one by one through them and explain what they are doing. The first one is the source SBOM that I want to explain. This is the file that explains for the source what went into the build, what are the licenses of the files. For that, we have some static analysis that, for example, looks for the SPDX license identifiers in the files that were used and extracts their license. It tries to guess the file type based on the extension and its location, like it's intended as a source file, for example. And we compute some file hashes and potential identifiers that can be stored in the SBOM to validate and to reference these files. An example for that is this. This is how it's actually serialized in SPDX. So it has a type, it has an internal ID. This is a globally unique ID, which is shortened. This S colon is a shorthand for longer identifier, which is defined in the context of this file. So it's like a abbreviation that is used. It has a file hash, it has this primary purpose source, and it, in this case, also has this gitoid content identifier, which is a standard to identify contents in a normalized way. And it has the file name, which is this init slash main.c. So that's the file that is described. Additionally, I mentioned it contains the licensing information, which is in SPDX separated from the actual file. It's linked to the file via relationship, has declared license, and that's how it would be encoded in SPDX. So the file is linked with this has declared license relationship to the license two package elements listed here. The first one is the Linux kernel, in that case, the BZ image. It has a comment that describes the architecture, just so we can fill metadata there. It has a primary purpose. It's an application, which is, I think, the best match in that case from the enum of primary purposes. It has a version, and if the ancestor of relationship to this high-level build from the previous slide. And just to show an example, that's one of the build steps in between. In the comment is the actual command that was used to generate that, or that was run with this build. It has input relationship that explains what were the inputs of this build step, and has output, explains that is the output, and that links the files from sources to build to intermediate steps to the final output. And that are the objects that in the end represent the build. Overhead was left out. But yeah, that's what we serialized. Additionally, and relevant is it's reproducible. SPDX has some things that need to be passed into it to make it reproducible. For example, UUID or something to make IDs globally unique. We support passing that from the outside, and build time that can be passed from the outside. That makes it reproducible and deterministic, the whole generation. And now what are the next steps? So the idea or the plan is to take our tool, not the whole repository that I had linked, but just the core functionality, which lives in the repository in the SBOM folder, and contribute that to the kernel sources under tools SBOM, and add a config option to enable that. And that would make the kernel build able to produce the SBOMs in the make build automatically. And that's somehow the idea. There's a hacky proof of concept for that. So my colleague built that already and shows that it works. I think it's by far not following best practices, but it's a good proof of concept. And so if you call the commands here, you will have in the end the 3.json files in the build output folder. And other than that, yeah, we are looking forward to have contact with the real world, to get feedback, and to see what you all say about the outputs, and whether it's usable, whether it, what are the downsides, what are the issues. It's limited right now to architecture-wise to x86 and ARM, but we want to extend that. That's related. So what's limiting the architecture support is the parser for the make commands in the make files from the beginning. They need to be written, so there are still some gaps, but that's work in progress. And we were thinking about how to integrate that into other tools, like if the Yocto build generates an SPDX file that references the kernel, that kernel reference could reference the very detailed SBOMs that we generate, to have that all in a big knowledge graph. That's my presentation. And now I would be open for the second round of questions.
Do you plan to have any way of enforcing, for example, license compatibility when loading modules?
We plan to have the default behavior that license information in the source code needs to be complete. So that's the input data, that it is complete, and that you explicitly need to allow missing license information. That makes the information complete, so that you can reason about that. Regarding compatibility, I think that's another tool that can consume the SBOM and analyze it. I think that we don't want to have that in this core tooling, since it might be opinionated, it might depend on use case, it might depend on how you distribute. And right now we try to keep it small and fairly focused on one use case. I think it's easy to build that on top if you have the SPDX SBOM to check for these incompatibilities.
Well, I was asking because then it means that each module should carry with itself internally also the information about its license, which I don't know if it already does.
I don't know, but we right now link back to the, or you have the information about the source and which source files went into that. And via that tree, you can.
Thank you. Thank you.
Are you capturing also the snapshot of the toolchain that you are using to build the kernel?
We are planning about documenting the version of compilers in the build. So the build element has support for encoding this as, and we are planning to add that, yeah. So it's a goal. I think it's not yet there. We are right now capturing the environment, but that just says GCC is GCC. It's not yet with versions, but that's the plan. Any other questions? Yeah.
Maybe a naive question, but for me, identifier of a kernel build was always a Git repository and a commit.
Mm-hmm.
So how is this better?
You mean a better identifier, or?
Oh, like why? Yeah, why the Git hash is not enough?
To identify it, I think it's not a question about not enough. It's this identifier should be added to the output. So the SPDX allows you to have multiple identifiers for elements. So the origin should be part of the document in the end. But even the same commit hash can be compiled in different ways on different environments. So it's a good identifier for that's the source, the state of the source, but it doesn't encapsulate all of the environment and all of the choices that might have been made. One might build an unclean Git tree, and then it's not sufficient information. That's why we are basing it on the file hashes as identifiers, and that's also required by SPDX to have these file hashes. But yeah, the ID of the commit would be a valuable identifier. Yeah.
I think one thing is like the Git hash doesn't tell you which config is used to build the kernel.
Hmm.
So that's clearly missing in
Yeah.
the Git hash. Probably there are more things.
Mm-hmm. And the build element actually, just this line here, has a config source URI. So it references a different element in the SPDX document that describes the config. So it has a way to encode what was the config that was used for that build. Okay, I see no other hands. I see no questions in chat. Then thinking might be done.
Thanks for first the speaker for the referee track. And we have a little more time. So let's start right on time. So we got about 7 minutes before the next talk. Hello, hello. Okay.这边就直接这里左右就好了。你有改吗？你有改，我们还有1分钟，你可以来得及改。你改了是吧？那你
就改了几个错字，其实也还好。
我就改了几个错字。
对，其实还好。
看看我们时间，要不我们还正常开始。Okay. Okay. So I do not need my laptop. I was planning to use my laptop for this, but yeah.
就改了几个错字。
那我就还不动了，然后我们这个左右就好了。
哎，好，行。
OK， 我们的时间。
Hello，可以。
Hello, you hear me? Okay, let's get started. Our next speaker is Tong Wang. Tong is a Linux veteran, expert of multiple kernel subsystems,
Right now, his latest title is the CEO of multiple registered companies. Today, Tong will talk about the multi-kernel. Let's welcome Tong to give his presentation.
Thank you. Thanks for inviting me and thanks for coming to my session. So my name is Kong Wang, and I'm a Linux kernel developer, and I'm also the founder and the CEO of multi-kernel technology. So today I'm going to discuss about the multi-kernel architecture. So this architecture brings the kernel-to-kernel isolation with elastic resource management. So let's get started. For a long time in my career, so I actually had this assumption for a very long time, and I don't think I'm alone. And I think this assumption is pretty much common because we believe in a machine we could only run one single Linux kernel. If we want to run multiple Linux kernel, we either require virtualization like KVM or Zen, or we need some specialized hardware like AMP. The reason why we had this assumption for such a long time, I believe, is because it's rooted in the design of the SMP. And in SMP, all the CPUs are managed symmetrically. So I think this is the core reason why we had this assumption. However, this assumption is this one kernel model is not the hardware requirement. And with multi-kernel architecture, actually, it completely invalidates this assumption. So multi-kernel actually runs multiple Linux kernels concurrently on the same machine with no virtualization, no hypervisor, and no specialized hardware required. So each kernel controls its own hardware partition. And the different kernels, they communicate with explicit messaging. So this is what multi-kernel gives us. And the concept of multi-kernel actually is not new. Actually, if you look into the academic research papers, there are a lot of papers in this area. So there are different names, actually. So sometimes people also call this co-kernel, separation kernel, or nested kernel. So in different ways, but the concept is pretty much the same. And let's take a look at a few of the previous multi-kernel research papers. So there are more than 1,000 papers. So I just listed 3 papers here. The first one pioneered the multi-kernel research is called Barrelfish. So it was published in 2009. So 16 years ago. So it's pretty old. And this design actually is based on the replica. So, and the whole system actually forms a single system image. And more importantly, this operating system is not Linux, so we will not discuss more about this one. However, this one is definitely pioneered the concept of the multi-kernel research. And the next one is Popcorn Linux, which is also the first one bringing the multi-kernel concept into Linux. And this one was published in 2013. And this one actually implements the process migration across different kernels. However, it still maintains the single system image. Even if you check out the latest papers they published this year, it's still the same. And this still focuses on the heterogeneous CPUs. So in my career, I have never seen such hardware in my career. And the next research I want to mention is the Mac kernel, so which was published in 2015. And this is another different one because actually it uses a 2-tier design. So it has a performance kernel and a service kernel. The service kernel is based on the Linux, but the performance kernel is a customized lightweight kernel from scratch, which is not Linux. And our design actually is pretty much inspired by the Mac kernel. And the Mac kernel actually is also significantly different from the last 2 is because it does not actually use a replica. So our implementation actually takes the similar approach as the mega kernel. So we choose isolation rather than the replication. So and the different kernels, they coexist as peers. We only need to distinguish them when we need to talk about the management duties, like the host kernel need to manage the life cycles of spawn kernel. Other than this, actually they are pretty much equal, like peers. And they run with a dedicated but elastic hardware resource. And because they are isolated, so each application runs their own tailored Linux kernel inside each of the kernel instances. And this is a high-level design of the our multi-kernel approach. So we have the host kernel, which is the booting kernel. So the booting kernel actually takes all the management responsibility. So it manages all the hardware resources. It also manages all the life cycles of the spawn kernels. And more importantly, it also coordinates between different kernels on the same host for the resource management as well. And the spawn kernels, they are started by the host kernel. And they should run the tailored Linux kernel to get the better performance and lightweight. And the actual application should be run inside the spawn kernel. And each spawn kernel has isolated hardware resources. And when they communicate, they use the interprocessor, interrupt, and shared memory. And so how is this different from the Mac kernel? So Mac kernel actually, like I mentioned, is a customized kernel for the lightweight. So we don't use any customized kernel. We just use Linux kernel. And the reason why we want a Linux kernel is because of the capability. So even with Mac kernel, they implement about 200 system calls. This is still less than half of the system calls supported by Linux. And I want to offer another additional argument when people want to implement an operating system from scratch, just want to compatible with Linux for system calls is Linux actually is more than just system calls today, because we have eBPF, so it's much more than just a system calls. So if you want compatible with the entire Linux ecosystem, to me that's impossible. So that's why we don't just use Linux as it is. And our approach is we use Linux as it is. So we just add the multi-kernel support to the Linux kernel, and to get the lightweight kernel, we just tailor the Linux kernel. This is pretty much done for the embedded system for many years. And another difference between microkernel and our approach is actually we reuse the key exec. So if you are not familiar with the key exec, so key exec is a mechanism in Linux kernel to load and unload the kernel image. So there is a system called key exec file load to manage all the kernel images. So we reuse this part, and there are two additional benefits if we reuse key-exec. The first one is we also get the kernel signing infrastructure once we support the file-based key-exec. We get this for free. And because recently the community also supports the key-exec handover, so which means if we leverage the key-exec, we also get a key-exec handover for free. However, we use key-exec handover slightly different to pass different information across the kernels. And and I think this also reflects our design philosophy. So we don't actually want to invent anything seriously. So we just want to reuse everything. That's our goal. And beyond the key exec, so let's take a look at what else we reused. So the interprocessor interrupt is also reused. That's for sure, right? So it's commonly used in the Linux kernel today. And to manage the physical memory, so I don't want to implement any physical memory allocator. So that's why I reuse the genpool allocator. It works pretty well. So, and to suspend and resume kernel, I don't invent anything new. So I just reuse the existing kernel suspending and resuming infrastructure. And in the future, actually, I plan to support the checkpointing and the kernel context switching with Hyperation infrastructure as well. I think that's doable. And for the user space inter-kernel communication, I actually leverage the VShock infrastructure to implement all the protocols on top of the API. So, and this actually deeply reflects our another philosophy. So we want to embrace Linux, and we embrace Linux by doing deeper integration with different Linux kernel subsystems. And let's dive into the most important part, the resource management. So before we move to the resource management, so there is one critical question we need to answer, which is also frequently asked questions I received from the community or from different channels. This question is, should we go with static partitioning or dynamic allocation? So from our perspective, static partitioning is too easy. So it's just simply the default state of dynamic resource allocation. However, the reverse is not true. So this is why we want the dynamic one, because the dynamic one is clearly more flexible than the static one. And also, let's take a look at the potential use case, like the cloud computing and high performance computing. And in this scenario, I do believe the dynamic resource management is not optional. It's pretty much essential if we want to make the resource utilization high, right? And however, we do have a challenge, right? Because the dynamic one is definitely harder than the static one. The challenge here is how we implement this dynamic. Meanwhile, we are maintaining the isolation. We take this challenge and we do have some solution. And I believe this solution is also elegant as well. And for the long term, I believe the flexibility will ultimately prevails. So this is also why I prefer the dynamic allocation. And so finally, let's take a look at the resource management. So resource management is, I think, is critical and is probably the one of the overlooking part in the academic research. And to solve this, actually, I take a look at the existing Linux kernel infrastructure as well. As you can guess, I don't invent anything here. So I just pick another thing in the Linux kernel infrastructure. It's called a device tree. So if you are if you are familiar with embedded systems, so this is definitely not new. It's actually pretty well established standard in the embedded system. So device tree is the interface used to describe the hardware resource for the embedded system today. And another reason, another benefit we use device tree for resource management is actually device tree also offers device tree overlay. So device tree overlay actually enables the dynamic hardware configuration changes at runtime for the embedded system. So for us, actually, this pretty much enables the dynamic resource changes. So this makes the device tree a perfect solution or a perfect interface for the resource management here for the multi-kernel. And another additional benefits we have with device tree is this could also avoid the fragile kernel command line manipulation. So we no longer need to manipulate the kernel command lines. And if you are not familiar with the device tree, so this is the example. Actually, it's a real example I use for testing. So in this example, I show you how I assign different hardware resources to a kernel instance. So this kernel instance is called a web server, and I assign I think it's maybe 1 GB or half gigabytes of memory to this kernel instance, and I assign the CPU with physical ID 1 to this kernel instance, and with the PCI device, which is actually a network interface to this kernel instance as well. And this is a device tree overlay to describe the change. So this change actually, the change I show here is how it is adding a CPU. So here I want to add the CPU number 2 to the kernel instance I just showed. So after applying this change, the kernel instance would have both CPU 1 and CPU 2. And of course, the device tree is just the interface. So underlying, we still need to implement the actual operation to make the changes, to update the hardware resources. So like you can guess, actually, I don't invent anything. So I just leverage the CPU, the hot plug mechanism. So Linux actually supports the hot plugging pretty well. So for CPU, memory, PCI device, it works extremely well. So how does the entire process look like? So if we put all the pieces together, so initially, so when the user space want to make some changes, the user space needed to generate a device tree overlay to describe the changes like I showed in the previous slides, and the host kernel needed to translate this overlay to the resource updated messages. And this message will be sent to the target kernel through the IPI and shared memory. And once the target kernel receives the message, they will apply the changes with the actual hot plug operations. And after this, all the resource update is complete. And of course, I simplify this a lot here because actually I assume we have sufficient hardware resource for allocation. However, for I/O devices, this is typically not true because for servers today we maybe have hundreds of CPU cores today. It's pretty common for servers. However, for I/O device, we only have a handful of I/O devices, even for servers, right? So how to solve this problem for servers? So maybe we can take a look at how virtualization solves the problem. So if you know virtualization, actually there is a solution called SIROV. So it's a hardware level isolation for the hardware device. So the hardware provide additional abstraction for the devices for each different virtual machine. However, the limitation here is the limited virtual function and also the inflexibility. And more importantly, actually, if we really want to use the virtualization, that means we need to touch the virtualization stack. It's not that we can just use SIROV directly without bothering the virtualization stack. So in this case, we probably need to bother ROMMU, which is pretty much what I don't want to touch. So what is my solution here? So the solution here is actually we want to use the hardware queue solution because the observation here is the modern I/O device today pretty much already support many hardware queues. So and with this actually we could actually just isolate and assign different hardware queues to different kernel instances, and how to share the hardware queues between different kernels. Actually, we also have something existing in the Linux kernel. So as you can see, I don't invent anything. So for networking, we already have AF-XDP, right? So AF-XDP is pretty much is binded with each of the network interface queue. And similarly for the IOU ring, there is a UBLK. I think we could leverage the UBLK for similar purposes as well. And they use ring buffer, and they provide the zero copy support, which is perfect for our case. And more importantly, actually, because we need to maintain the cross-kernel compatibility. So, and XDP and IOU ring, they actually offer the user space APIs compatibility, which is even stronger than our case. So, which is much better. And more also, actually, speaking of the resource management, the dynamic queue assignment is definitely much faster than the resource allocation. And let's take a look at the concept here, because I don't have any implementation here. So here is just the concept. So I just draw some diagrams here to show the concept. So the host kernel will establish everything, with XDP infrastructure, establish the ring buffer and bind the ring buffer with each of the queue, and map the ring buffer with the spawn kernel. So inside the spawn kernel, we need to implement a simple software networking device, which actually retrieves the data from this shared ring buffer. And also we also need to use API as a doorbell to get to simulate the interrupt, the TX and RX interrupt. So this is basically how this works. And similarly for the storage, actually we use UBLK. So UBLK is based on the IOU ring. So it's pretty much similar to the concept of the XDP. However, storage is harder, definitely, that's for sure, because for storage, we do need to have the backend storage to store data, right? So that's critical. So that means the data itself also needed to be isolated. So probably we could actually leverage the logical volume manager to manage the disk isolation. And on top of that, I think we could actually establish a UBLK server in the host kernel, and also inside each of the spawn kernel, we just implement a software block device, which is as a UBLK client. So we should use the shared ring buffer to communicate with the UBLK server. So this is also just a concept. I don't have any code yet. And let's talk about the use case, because people care about the use case a lot, that's for sure. And I have 4 use cases actually. So the first use case I have is the cloud computing. So cloud computing today, we have 2 different technologies used for cloud computing. The first one is the container. So compare with container, how is the multi-kernel isolation compared with container isolation? So the container isolation is resource level isolation provided by the kernel. However, the multi-kernel isolation is kernel level isolation. So they are significantly different, because the kernel level isolation actually provides stronger isolation. That means the performance actually is also isolated better than containers. So what does this mean? This means we could also eliminate the noisy neighbor issue in the containers. And also because containers, they share the same kernel. That means there is no chance we could actually build a lightweight and tailored Linux kernel just specifically for application, because different containers run different application. However, for multi-kernel, this is definitely doable, and actually this is what my plan is. And with this approach, actually we could achieve the reduce the OS noise like the Mac kernel does as well. And with this, I do hope we would get a better tuned, optimized, and highly customized Linux kernel for each specific application. And ideally, this is automated. And another technology in cloud community is virtual machine. So for virtual machine, the difference is we don't have hypervisor, that's for sure, and we don't have virtualization overhead. So if you don't believe virtualization overhead, I do have more points for you. So for virtualization, actually, we have a single point of failure, right? So the host kernel is your single point of failure. So for multi-kernel architecture, there is no single point of failure, that's for sure. And the entire technical stack is much simpler. So I didn't have time to draw the virtualization stack, but I can imagine it's much complicated than the multi-kernel technical stack. And what does this mean? This means actually for security, this is significantly reduced attack surface. And another advantage actually is for the resource management is definitely much more elastic than the virtual machine, because we don't have any hypervisor layer. And the startup time is also faster because we just boot directly to the init process and get rid of everything else. The second use case I could imagine is the live kernel update. So what do we do to update the kernel today? So today, actually, pretty much most of the case, we just reboot the kernel, right? Sometimes we just use live patching or the kpatch to avoid reboot, but probably in most cases, we just still reboot the kernel. And because of a reboot, all the applications need to be interrupted. And what does this mean is if you are manage a large cluster, that means you need to schedule the kernel updates, and that which also means you need to have redundancy, to have the redundant the scheduled kernel updates as well. And recently, actually, the Linux kernel community actually also proposed a live update orchestrator. So this one actually is pretty good. So it's based on the kexec as well. However, because it's still based on the kexec faster reboot, so it definitely reduces the downtime, however, but it does not completely eliminate the downtime. So all the processes definitely need to be paused during the kexec transaction. And more importantly, this transaction is either all or nothing. So there is not nothing in between, and we can't go back. So how does multi-kernel differentiate with this one? So because multi-kernel, we could actually run the multiple kernels concurrently. So what does it mean? This mean is we could actually boot the new kernel together with the old kernel, and we gradually migrate the process from the old kernel to the new one. And until all the processes are migrated, the old kernel can be just simply retired, and the new kernel will simply take over all the resources on the machine, and the entire kernel update would be complete. And more importantly, actually, we could also support a rollback. So at any point of the checkpoint, we could actually just roll back to the previous. So this is pretty convenient if anything happened in the middle. And with this, I do hope we could really achieve zero downtime kernel update. And another use case which is pretty much similar to this one, but however it's not exactly the same is the kernel crash or healing. So what do we do today? When kernel crashes? So because let's say if we have the kdump. So if we have kdump, the kdump kernel will take over the machine. Once the kernel crashes, so the kdump kernel will pretty much just capture the VM core of the crashed kernel, and because the kdump kernel is very minimum, so it's not sufficient to run serious production services. So that means we need to do a second reboot to the normal kernel to get it back to the service. So that means we have to reboot twice. So this probably means minutes of downtime. However, with multi-kernel, this is actually much easier. So we just start a backup kernel, pretty much like the kdump kernel, and running in parallel with the regular kernel. So the backup kernel will regularly detect if the regular kernel crashes or running normally, during with some hard beating mechanism. And once it detects the timeout, it will immediately take over all the hardware resources. And also, actually, it could also restore the process state from the preserved memory if you prefer. So this could actually resume, I estimate the service in a few seconds. So this is definitely a significant improvement. And the last use case is not as wide as the previous one. However, I think is probably people in this room are very interested in the kernel live debugging. So what do we do for kernel debugging today? So let's say if we want to debug across the kernel, pretty much we use kdump, right? So kdump is very commonly used for the post-crash kernel debugging. And for live kernel debugging, we pretty much rely on the key core for the running kernel. And for the running kernel, it's impossible to pause the kernel unless we have some external debugger, whether it's external to your virtual machine or external, with some hardware, right? However, with multi-kernels, you don't need that complex external debugger. You just need the host kernel and the spawn kernel. That's all. You don't even need a debugger, pretty much, in some way. So how does this work? So we could actually use the host kernel to debug to inspect the spawn kernel, and the host kernel could also obtain the key core through the multi-kernel file system directly of the running spawn kernel. And more importantly, the host kernel could also pause and resume the spawn kernel execution at any time. And of course, there are also some drawback of this architecture as well. So the security model actually is pretty much a major drawback here. So for multi-kernel, we actually have to trust the kernel. So each kernel is trusted to honor its resource boundary at least. And what does this mean? This means the kernel must be trusted. It's not a malicious kernel. And so with this security model, if we don't make any improvement, that means if we use it today, it is still suitable for the cases like a provided cloud as well. So the trade-off we have here is the performance over absolute security, and I don't believe in absolute security. And of course, we can improve this, right? So, and I do hope the hardware vendors could also help us to improve the hardware resource support for the isolation. So the first one I could imagine is the hardware vendors, the CPU vendors, they could actually support the memory protection, like, with bounded memory pointers, with enforced ranges, memory tagging, maybe something like this. I think that that will help a lot for us to protect the memory isolation of multi-kernel architecture. And another CPU improvement we need is the IPI. So we want the hardware vendors to provide the hardware filtered IPI, because currently any CPU could send the IPI to any CPU, on the same in the same node. And of course, we can use software to do the filtering, but that has overhead. And of course, on the there's another thing actually, which is not my expertise, is confidential computing. So confidential computing actually support is also what we need to be competitive with virtual machine. However, the hardware support for the confidential computing, based on my understanding, is still not very ready for the multi-kernel architecture. And I do hope we could actually collaborate together with hardware vendors together to make this happen. And last but not least, I do hope the I/O device vendors, like the storage, the networking device vendors, we could also improve the hardware queues as well. For example, the NVMe device, they already support the namespaces, which is pretty good for the storage isolation. However, we also want the queue isolation as well on top of the namespace. I do hope they could provide some kind of a controller partitioning. I'm not sure if I use this term correctly, but that's what I would like to propose. So that's pretty much I have, and I know this is a lot of information, and I do. And I think I talked a lot today. So, however, there is one famous quote is, talk is cheap, show me your code. So, where is the code? So here is the Linux kernel code I shared on GitHub. So I also posted this code to the Linux kernel mailing list as well. So feel free to check this out. And more importantly, actually, we are more than just a Linux kernel. So in the user space, we definitely also need the orchestration and management tool as well. So I implemented this tool called Curve in the user space as well, and it works pretty well. I also have some demos for this as well. And for the kernel crash auto-heating and kernel lab update, so I started another project called K-Morph. So I do hope this project could transform kernels without actually any reboot. And another project I have actually is related to kernel customization, is called kernel script. So this is a programming language I hope to simplify the eBPF development, because eBPF today is becoming more and more complex. And I do hope with this programming language, we could actually significantly simplify the kernel customization with eBPF. And in case you get lost, so this is, I hope this one could provide you a clear picture of what I want to achieve eventually. And this is how I architect the entire multi-kernel ecosystem. And in case you wonder, maybe today I give you a lot of answers than questions. Actually, it's all the opposite, because we are the Plumber conference. Actually, I have more questions than answers. Actually, the questions are for you, and I do hope my talk could inspire you for your creativity, and I do hope you could give me better answers to my questions. So I do have more questions here. So if you are interested, actually, maybe each of the questions could also turn into some, research paper as well. So if you are interested, we could actually publish some research papers together as well. And I do have some researchers interested in collaboration. So if you are interested in joining, you are very welcome to do so. And okay, that's pretty much I have for today. And if you have any question, any feedback, or any suggestion, or you want the collaboration of any form, research or development of any kind, feel free to reach out to me with this email. And we also have, some other channels for communication, like Discord and mailing list. And more importantly, I also have video demos, which I don't have time to show today, but feel free to check out our YouTube channel. And last but not least, that's pretty much all I have today. And thank you so much for listening.
So we have a raised hand from remote attendees. Can you unmute yourself and ask the question? Hello.
Can you hear me?
Yes, we can hear you.
Okay. So you have already gotten some feedback on this when you sent patches. It's been said that...
Can you speak up a little bit?
Yeah, I'll try. Is this better?
Yes, it's slightly better.
Okay, I'll try to speak as loud as I can. It has been said in the networking community, those that don't understand TCP are bound to reinvent it poorly at the wrong level. This is reinventing paravirtualization at the wrong level. And we have not gotten any indication that this is fundamentally different. You are losing a lot. Your management kernel is directly equivalent to Zen's DOM 0, except that without the underlying hypervisor, you don't have CPU you don't have kernel to kernel isolation, because each kernel has full control over the machine. I think you have a very, very hard burden of proof here, and so far I have seen absolutely no evidence that any of this is motivated. Paravirtualization is something we've been trying to get rid of for 20 years because it shifts an enormous maintenance burden onto the general Linux development community. It is a huge impact on it's a huge impact on the maintainers, and this is.
So I'm afraid. Sorry to interrupt. I think it sounds like a long comment that we cannot address within this session. Would you mind taking it offline?
Yeah, I mean, it's already been discussed on LKML, and I guess that the conversation needs to continue.
Okay, thank you. We have questions from remote attendees. Does multi-kernel isolate a crash from one instance to another, and how?
Oh, yes, this is a good question. Actually, I have a demo on YouTube channel to isolate the crash isolation. So how this is done is actually I isolated the I think it's reboot vectors. So so that when the kernel crash, it will not impact others.
There's one more remote question. How are physical CPUs scheduled to be the virtual CPUs of multi-kernel?
The CPUs are not scheduled, so they are completely isolated. So this is why we don't implement the overcommitment yet. However, if we could actually implement the kernel switching, I think that's also doable to schedule the CPUs for kernels.
Hi, it's Jason. So I'm the KXZ Hanover developer. So I'm happy to see there's a new use case as a multi-kernel to use the KXZ Hanover. But the whole idea of KXZ Hanover is like we want to pass the preserved memory to the second kernel. The second kernel, when boot up, it know nothing, but not touching those preserved memory. So in this case, it looks like all kernels are like are online together, and the memory is already live. So what kind of information you want to pass from the host kernel to the spawn kernel through the KXZ Hanover? Would you like give me more information about it?
So you are talking about the shared memory between different kernel?
I mean the KXZ Hanover. You use the KXZ to like put the second kernel, right?
Oh, okay, yeah, that's a very good question. So what we pass using KExec Hanover is the device tree. So because I use the device tree to describe the resource. So when we start a spawn kernel, so I need to pass all the resource information to that kernel as well.
But the kernel already has a base device tree that it gets, right? So can't you just put the information there?
Sorry, I didn't hear.
So my question is, the kernel already gets a device tree, right? So which is where the KHO device tree also resides on ARM64, for example. So can't you just use that to encode the information?
Sorry, I didn't hear.
Can elaborate more.
Okay. I think Pratyush said that KHO already passes a device tree like as part of its own operation, right? It has a KHO root device tree, and ARM has its own device tree for the devices.
Just pass the information through the main device.
Okay, so Pratyush is saying that the ARM has its own main device tree, and then the KHO is passed through that main device tree already on ARM.
Oh, okay. So I don't implement the ARM part yet. So
Okay.
so far it's only for the x86.
I have a question too. So,
Okay.
I think what Peter said is very crucial to answer, because really there is no isolation. It's like the cloud use case, I don't think is doable without having any isolation story. And then the isolation story is the hardware virtualization that we have, and that brings the overhead down to, like, on very well optimized VMs, to 1% or less. So again, I really don't see the cloud use case. Regarding the other ones, live update or debugging. So debugging is a very good example. I don't know if it really works, like implementing all of this for the debugging purpose. It's very similar to the way MDB is implemented in Solaris, where you have a different debugger that allows to inspect the running Solaris instance. So in this case, yeah, we can have a minimal partition that performs a step debugging of another running partition, like just to study some very specific cases. But I mean, Linux we have virtual machines, and I'm not sure if that's use cases that necessary. Maybe there are some corner cases where it's useful, but again, for live update use case, so I was looking at something similar some time ago, but I found that it's very hard to share a global machine state such as Epic or something like an interrupt controller, right? How are you going to share between the two kernels safely, even for a very short period of time of live update? So I think there are other approaches that we can take to make live update seamless instead of having two kernels running in parallel. But I might be wrong. I mean, that use case can be studied, but again, this global machine state is very scary to me. So,
thank you.
I think maybe the simpler way to do this live update is have like a lightweight hypervisor in between for the transition. That might, like, if you can service enough syscalls or hypercalls.
I think it's simpler to keep the CPUs running and not pause them during the kexec, just the orphan VMs. That's
So it's going to reduce the downtime.
Yes, yes.
Okay, so my question is that, do you have read the implementation from NetBSD, because they have the very similar implementation called rump kernel that it tries to make a children in NetBSD running on existing NetBSD, and they have this kind of called rump core, which is basically the business version of the hypercore. So the children NetBSD could implement its own device driver and initialize and deallocate the hot plug-in hardware. So so that my question is that, how do you handle the hot plug-in device? Like the host kernel needs to take over it and pass through to your multi-kernel, or is it completely taken over by your multi-kernel client? Thank you.
So sorry to interrupt. We're already like 5 minutes over time. So I think we got a lot of very interesting discussions going on. So let's take that offline. This is all Plumbers about. You meet people, you go to the hallway, hopefully we will resolve something. Let's give another round for our speaker. And so we have a break right now. Let's come back to the next session you want at 12 o'clock. Thank you.
No, I think that's kind of similar to Yeah.
So we don't care about the current here, but we care about we don't want your computer to good or have a separated stack of about something like that. But I'm not sure whether because you're using the whole framework or
Yeah, I will email. Okay, thank you.
Yes, it's like anything, but at the socket level, we are sacrificing at least a thought, right? So we do not really like zero performance.
Yeah.
Right? Do have like one problem away.
Yeah, and I think the curve actually learn all the CPU topology and allocate the CPU based on best all the best
Zero count and that we assume that the process interface, right? Unless the process terminates, you can't explain you kernel like in the process and not get that right. So like one question, like we say like if I have correctly, you say that we are going to bring down the kernel, start again the process, and you can.
No, that's not it. Actually, I want to process the block. That's what I need here. But otherwise, we checkpoint the process and we already have checkpoint and this. Yeah. Yeah, that's
You are saying that the virtualization has to come. So the current memory, and especially the failing part, is it better than the hardware assisted virtualization features like NVIDIA? Because I'm not sure about the implementation, but wouldn't there be like double faults or something? It's just a trust that the other government is not going to touch.
Yes. Yeah.
No, they're not sharing the same page tag. They have their own page tag. They're not sharing page tag. Like each product has its own page table, and the entries in those page tables represent like a subset of physical memory. And it's just trust that this kernel is not going to mess with the and then trust. So we can assume that the host kernel doesn't use requirements and that will page tag. Yeah. First point was like it's like KVM is pretty much transferable. You have a multi-kernel would be like a thing. In some sense, I would love to have a one side part of it.
So what you I think you mentioned it. Most of IPI that start up smaller, give it a subset of the hierarchies, and then and then like your networking task is on hardware hierarchies. That's what's there's some arms and some force But the cherry stuff is actually also great. And then this five, some cherry hardware is going to go. Cherry, but get some isolation. Hardware is super isolation. But the main problem with this is you're going to cherry. But I mean, it's really valid. always a trade-off. Yeah, after you talk, I do, yeah. Yeah. Yeah, so I'm a consultant. This company's a consultancy. So we do mostly hardware, embedded consultancy. Yeah. Oh, okay. Good. Let's go ahead. Yeah, I'm Kate Hilton.
Are you speaking this time? Okay. That sounds like a lot of work. Okay, already. 80%.
Ouch. Time.
So you want 25 minutes each. Basically 25 minutes each. You also want like 5 minutes for question. You want 25 minutes for okay. You know the right now everything's presented from the back. We are not presenting from okay. That's not just Why? Have a video somewhere we share that and show it. I mean, whatever you want to show, if you have a video of it.
We wanted people to play. Oh yeah, we have a demo. Is that possible? Just give us an HDMI cable.
No, the system. One thing we can do.
I'm all curious about this device. Have a booth. Have a booth downstairs. You can actually play with the controller. It's more than the triangle that I brought.
Log in to this website.
Yeah.
And we will try to like share from over there. Like we wanted to play. Guys, okay, like what we usually do here.
Yeah, but yeah, you were expecting to just get an HDMI. Their system is like you have to doing the web thing for
Basically, you have to connect to a streaming server. We should get started. Yeah. We have the Snap-on Mac if you want, or you can use that one. Right. Oh, that one. Whichever you like. So we have that one already work.
Okay, good. I mean, if this works, fine. But sometimes I move, but this I cannot move much. I don't know if it works. Maybe good. More people have used it, or people use
it works.
What people is using? Yeah, let's try to do this one. Oh. Can we try this one? Maybe? You can put it wherever. Hello? Hello? Yeah. I think it works.
Hello, welcome back. And so next we'll have Miguel. As we all know, whenever he show up, we'll talk about the Rust for Linux. So take the stage.
Thank you, Song. Yeah, welcome everybody. Thanks for joining. As usual, I use this title. I always talk about Rust for Linux, so I keep using and reusing this title. I'm going to give you very quickly. I will probably not be able to go through everything I have in the slides, but I will give you like the latest news. That's what has happened. What I think is important for everybody that is interested in Rust in the kernel. What is important since the last LPC. Then I will mention what just happened yesterday, some news, and then a bit of the future if we have time. And then that's it. There is also some backup slides that is, with more content if people want to go through it. So let's get started. The latest news, as I said, I will give you some headlines. Greg presented these numbers, these figures about Linux and how many people and how many commits and how many developers and companies, etc., contribute to the kernel. And I put these figures here because I want to compare them with the Rust for Linux ones, right? So, for example, in Linux we have 1,800 unique kernel maintainers listed. We have 2,000 roughly developers in a single cycle. So for comparison, and these numbers are since the beginning, okay? It's not exactly a one-to-one comparison, but so that you have some perspective of what has happened, we have had 2,500 patch series, not patches, but patch series in Rust for Linux so far, with 300 submitters of unique submitters of patches. There is, of course, many new people there that maybe submit one or two patches, so the distribution is not, it's like, has like a tail, but it gives you an idea. We also had, before we were merged into the kernel, we had 700 PRs on GitHub early on. And then also, of course, we have a lot of other work in other projects, for example, in upstream Rust, and I will talk a bit about that. So it's not just the work in the kernel. Rust for Linux is also about other projects as well, because it requires a lot of work on the toolchain, on other tooling, etc. We so far had more or less, or roughly 100 PRs, to give you a round number, to Linus Torvalds directly, and also other PRs to other maintainers that then send to Linus the PR, the aggregated PR. We have about to give an estimate on because sometimes I see people in forums and so on wondering how many people is around, right? And there is all this news about, oh, people is leaving and so on. I mean, we have 20 in the maintainer file. We have 20 entries explicitly about Rust. And then there are other subsystems that I am not counting there, which also maintain Rust files on their own, right? In the normal entry they use for the C side, so they also maintain the Rust side. But just the ones that explicitly say Rust in the title of the entry is 20, and there is inside those, if you take all of them and then you sort on unique, do the sort unique of that list, we get 30 people, maintainers and reviewers of those entries. Okay, so there is quite a lot of people involved already. And we have around seven active core members, and we are expanding that with some reviewers in the future. So community, because it's related, I usually give this graph every year, how it's going. The curve is essentially going up roughly the same way. We almost double the number of messages since last time, as usual. We also have this graph that I like to put always there because it shows the news. So it's like Herbit, and when you see spikes, it's the news. So I tried to get this graph like yesterday night. I updated it. I didn't see the spike yet, but I'm pretty sure we'll get another spike due to some news I will give you later. Who uses Rust for Linux? I'm going to go through a few of these that I think had some important progress, and I think it's important for what I will say later. So first of all, the DRM panic QR code generator. In a conference in Rust Week, I think it was, I presented this. I looked for users of that in production, and I saw this Reddit post by somebody that had a kernel panic, right, and was asking, well, how do I solve my issue, right? Maybe they didn't realize or not, but they were running Rust in the distribution. So Arch Linux, for example, was running Rust in production, and there is a use case there, which is, when you have a kernel panic. Of course, I don't want people to get more kernel panics, right, just for running Rust, but is there, right? And this was important when I mentioned it like half a year ago in that conference in Rust Week, but now we have even more things that are more important. So the Nova GPU driver, there has been a lot of progress there. Danilo, sadly, of course, the Nova GPU driver, for those that don't know, is for the GSP class GPUs, the NVIDIA GPUs, and it's upstream. It's being developed there, and Danilo is doing a ton of work on the GPU, the DRM abstractions, and also other abstractions, device, driver core, etc. Danilo couldn't make it to LPC because he got sick at the last minute. He couldn't take the flight. So I put this slide that he gave me for a previous conference recently, so that you have at least some bullet points from him. And I think I asked the organizers, the LPC organizers, to see if maybe he could record the talk later in a week or two, and when he's recovered, and you can hear about Nova and other things he wants to talk about, like maintenance. Then the tier GPU driver, the other one, right? The one for the Panther one. I was going to, so Daniel, who is there, gave me some slides, but now he actually has the chance to speak about it, and he will give a very cool demo, which he's preparing right now. I encourage you to stay here in the room because he's speaking right after. Android binder. So Android binder, the Rust version of Android binder, has been merged for this cycle, for the just released kernel cycle. This is an effort that started even before we were merged into the Linux kernel. Wesson, my co-maintainer back then, he developed the original version and so on at Google, and then this continued until 2-3 weeks ago, when it was merged finally into upstream. So we have now Android binder. It's not yet used in production in phones, but it's there. Now, this was important, very important, because it means that people will get to use it soon, but we don't know yet how soon. But the other big piece of news is on the outside, out of mainline users, there is another Android one, which is ASMEM. Okay, and ASMEM, that's, I think, the biggest piece of news, because just 2 weeks ago, disregard that. So ASMEM is now in the first production user in Android, and is in the Android 16, 6.12 kernel. That means it's now there, as soon as new phones and people get updates for their phones in Android phones, in a few months, we will have millions of users in the wild, right? In phones everybody's using. So it's millions of devices using Rust for Linux in the coming months. This is the news that we were waiting for so long to give you. So we thought it was going to be under Android binder, but in the end it was Hasman, the first one. And this is, I think, probably the biggest news. And the other one I have for you is the Debian kernel. 2 weeks ago, and this is the one sorry for the mistake. This is the one that I wanted to mention about the 2 weeks ago. 2 weeks ago, I got a tip from Noisy Coil, who told me that Ben and Bastian, which are part of the Debian kernel team, just merged the PR to enable Rust in the Debian kernel. So that's part of the PR, and this means you will have it available in SID, in Debian Unstable, in the coming weeks, as far as understood Noisy Coil. Then eventually we will have it in Forky, which is the next Debian stable kernel. And through stable backports, which is opt-in, we will likely have it also for Tixi, the current Debian stable. So yeah, that's huge because it's not the first distribution that enabled Rust. We had Ubuntu, we had Arch, we had Fedora, which are all of those have it enabled. I think Nix as well. But Debian stable is like the one that you want to hear, right, when you start a project. So Debian stable will have it. Unless something major happens. So that's amazing news, I think. Next, lines of code, lines of Rust code in Linux. I usually give this also as a measure of the progress we had. If you see there, well, I have there next from 10 days ago, but it's essentially what is going to appear in 6.19 in the next release. So you may wonder two things about that graph. The first one that I explained other times, that we had there a drop, a small drop, in that graph at least, which was alloc. We were vendoring alloc so that we could customize a couple of things from the standard library. So we dropped that, and the graph went down. But then we have like it's double. The last release is going to double the lines of Rust code. Of course, what does it mean, right? What does that mean? So we vendor in this release the scene library. So the scene library, for those that may not know, it's a parsing library. So it's meant to be used essentially for proc macros, to be able to write proc macros more easily. It's the most downloaded Rust crate out there. It doesn't run in the kernel. Just to be clear, it doesn't run in the kernel. This is just a user space library. It's like a compiler plugin, if you will, right? This library runs in the compiler to process the Rust tokens and output, whatever you want, as a token stream as well. And yeah, we will use it to write our macros more easily. In pinning we really needed it because Benno really wanted to. It's the macro that we have now, which is a declarative macro, is insane. He made it work, but it's insane. And with Scene, it's much easier to handle all these things. And we'll also use it for other macros. And there is Yang, sorry if I mispronounce the name, Jason. He's working on porting some of the macros that we have in MacroScript, and also Ben, I think, worked in the past on that out of 3. So yeah, we will have Scene, and that explains the huge bump. Now, if we remove all that code, because it's not really kernel code, right? If we remove all that code, all the vendor code, so both alloc in the past and now Scene, if we remove all that from the graph, we get this graph. This is the real kernel code, okay, the real Rust kernel code. So that's how it looks. I cannot go forward. Now, LPC 2024, so last time I was here, we were there. Because maybe, like, just to give you some context, the last time we were there. And now, a year later, or more than a year later, because this LPC is a bit late during the year, we have more than 4 times the code in the kernel. In fact, it's almost 5 times the Rust kernel code. I put a bar there so you can graphically see it. This is another of the headlines I wanted to give you because it's a huge amount of code that we are exploding. Essentially, with the DRM work and other work is exploding. The amount of Rust code we have exploded. And this is the exponential fit I used to do. I did it in the past. I don't know if in LPC, but I did in other conferences. That this is the exponential fit. This is still exponential, more or less. Of course, it will not remain like that, but it's just to show that the growth is huge. So what do we employ those lines for, right? What do we do with those lines? I cannot go into the details. It's too many things, but I usually put this slide with some past series that have landed in different releases. For example, in the last one, we got the LKMM generic atomics, the scene support, the module parameters, some types, driver core work, etc., etc. Collaboration with Rust. There are several headlines here. I think it's important to highlight this. So to give some context, since the early 2024, we had regular meetings. We have had regular meetings with upstream Rust, essentially bi-weekly. Every 2 weeks, we meet face-to-face with them, with different teams. Mostly the language team in Rust. Rust has a lot of teams. It's mostly the language team, but also the compiler team, the RustDoc team, Clippy team, Rust format. Not so often, but we also talk to them. And Rust for Linux has been a flagship project goal in the upstream Rust. A project goal is essentially what the Rust project wants to highlight as a priority for them, or at least as a goal that they want to achieve, right? We had those goals in the past, and now we are, thanks to those goals, we are very close to having Linux, the kernel, using only stable language features. And in fact, only one is allowed to be globally used within the kernel. The other features are just for the kernel credit, which is like the very core part that we use. So we don't have somebody else accidentally using unstable features. This is a common question we get where, oh, if what happens to a kernel developer, starts using an unstable feature because we enable those, right? We need those. So you cannot. You will get a compiler error if you try to do that. And I have some updates there that we don't need to get into. And now, for this half of the year, for the last half of the year, we got more project goals. I proposed the compiler feature goals and the language feature goals. So we have two, one for compiler, one for language, this half of the year. And also we have, in addition, other project goals, like the field projections one, the in-place init one, and the build STD. The first two of those, field projections and in-place initialization, actually are being worked by, or led by, people from the kernel team. So Benno, right there, Alice, and others are working, Xiang as well, they are working on those features. So what I'm trying to say with this is we have a collaboration that is not just that we ask for features, that also there is people in the kernel that can influence to some degree the future of the Rust language to make it good for the kernel. So this is great, this is amazing. It's like having, to compare with the C and C++ committees, it's like having people from the kernel working on the C++ and C committee, which as far as I know, we have a few, like for example, Paul McKinney, but really we have a direct channel with upstream Rust. I have, I have a couple of slides from Benno summarizing the field projections update. So this one is for field projections. As far as I understood Benno, there is very good progress, and we may have an RFC in the coming months. So that's great. We really want to have this feature. And then in place in it, we also have some progress. It's more complex in the scope. It's getting there are many solutions that need to be evaluated, but there is also progress going on there. So thank you, Benno, for the summary. Then Rust format, we had, or you may have heard that we had Linux wanted to, when Linux resolves merge conflicts, there are some that are really trivial, and it's a bit annoying to have just the import blocks, right? The use create or use kernel or use whatever. Rust format by default, it has an algorithm to format it that is visually nice, but it increases the rate of conflicts, right? The chance that you get conflicts. So Linux didn't want that, and we decided, hey, let's have it one per line. The problem is, to do that, you need unstable Rust format. And the problem is, you cannot enable that feature. And I asked years ago, but it was not possible. They didn't want to commit to be able for us to enable the unstable Rust format. So I look around, and I found out that if you put a comment in there, then what Rust format does, the logic it uses, the algorithm it uses, is essentially what we really wanted, which is splitting one per line. So yes, it looks bad, if you will. It's a hack, but it actually does what we want today in a stable Rust format. So Linus agreed to do this. He's happy with that. So we will have these slashes, and we are working with upstream Rust format to solve that. In fact, upstream Rust, due to this, created a new subteam of contributors to speed up development and to try to get through the backlog. And Manish gave me an update there. So yeah, there is people working on that. Also, Xiang is involved in that. And we are going to try to get through that. And eventually, what we want is to be able to just remove the data slash, that ugly slash, and everything else remains the same. Another example of collaboration with Rust is Clippy, the linter. So Alejandra in Cangrejos, which is the Rust for Linux conference, announced that Rust for Linux is getting first-class support. So as a volunteer, but she is committing to try to get the features we need in Clippy for the kernel, even if it is only us using them. Like, for example, the panic comments that we want to have checked by the linter, the ordering comments that we want to have, etc. So that's great. I really appreciate that people steps up in the Rust project to commit to help us. Another one is RustDoc. We have some features in RustDoc that Guillaume and his team is working on. And in fact, Guillaume is a good example here for collaboration even more deeply, because Guillaume he was new to the kernel. He didn't do any kernel work, but I asked him, hey, can we get this feature, which was meant to replace a hack I wrote to support the RustDoc doc test. So in the kernel, when you write in a function, documentation, if you put an example in Markdown, you just type an example in Markdown, then that is a KUnit test, and it's run actually, and the asserts is run, and the asserts are mapped back to the KUnit framework. So I wanted to remove the hack I had to do that, and now we got the feature. And Guillaume also sent the patch for the kernel to start using it. So that's great collaboration, because it means that upstream kernel upstream Rust people can get into the kernel. So it's both ways, the collaboration. Now we have Linux. I announced yesterday that we had the Linux kernel built for every PR in the Rust CI, in the compiler. And I also said that Bindgen would get it as well. Bindgen is the tool that we use to read C headers and generate Rust bindings. And now it happened as well. It just happened actually, I think the very same day over the list, the next day where I announced that last LPC, it actually got merged. So it has been a year where we got that, and it has been very nice. It has been working very nice. Rust C code GCC, this is the backend in the Rust compiler to use the Git library in GCC. Anthony, who leads the project, gave me this slide on what has happened in 2025 and what is going to happen in the next year. One thing I wanted to highlight, for example, is that they are working on let me see, here in the bottom of this slide, they are working on getting even new platforms like the Motorola one, which is great. This is an example of what you can do with the GCC support there. And yeah, Anthony is also working on the CI to have eventually the kernel as well on the GCC backend, not just the LLVM one that we have, as I just said in the previous slides, but also on this backend. So eventually we will get there. And we already have a CI, Anthony and I, where we work on that. GCRS, this is a big one, because I thought they were maybe far from this goal. But Arthur told me a couple of days ago, there is very good progress on compiling the kernel with the frontend, the GCC Rust frontend. And in fact, they said they will have more information at the beginning of next year. So that's, I think, this was when I mentioned it yesterday in the Maintainer Summit. I think this was an important point. And yes, I am eager to see it working for the first time. They have some issues with compiling the standard library. So the problem really that they have is compiler core, which is the standard library in Rust. It's not really the kernel crate. The kernel crate is easy. The kernel code in the kernel to build that is easy compared to the core crate. So as soon as essentially they finish that, the compiling core successfully, then the kernel goes afterwards. So very good piece of news. Cosinel also had progress, and Tathagata presented in Cangrejos a tutorial on Cosinel. So he's getting, he presented actually a tutorial, and people in the conference actually tried, and we went through it. And it actually is working, so it's useful already for some tasks. So I encourage you to try it out if you are going to do Rust in the kernel. Then we also had Cangrejos. It's another news or headline. We had, again, Cangrejos this year. As usual, a lot of people there chatting and presenting. We also had a poll. I ran a poll on asking. I asked many kernel developers, Rust upstream people, in general, stakeholders of Rust for Linux, right? Users of Rust for Linux. I asked in the keynote, in the first keynote, I presented in the first keynote, hey, these are the results of that poll. I asked some questions to people, and I got a lot of replies. If you go to that link and you download the presentation, the PDF, you will see a lot of quotes from people that you know, from kernel maintainers and other people that you know and you will recognize. Like, for example, I quote here Jonathan, but this is just one of the quotes. We have a lot of quotes. So if you are interested in thinking, in seeing what other people, maybe in this room, think about Rust, please go there and read the quotes because they are very, very interesting. I just highlight, as I said, this one from Jonathan. And all this news led yesterday to essentially the Maintainer Summit, where I proposed, well, I think maybe it's time to remove the experiment tag on Rust in the kernel. And we got the news. Jonathan published the article, and then he had to add a parenthesis there because people was complaining that it was a bit misleading. But yeah, so that's the very big news. We made it. Rust in the kernel is not going away. Everybody in the room actually was very positive yesterday in the Maintainer Summit. There was no complaints. People was eager to start using it. So I'm very proud and very thankful for all the support that we got. Thank you. Thank you. Thanks a lot. Yeah, I know what to say. Yesterday in the Maintainer Summit, to give you some context, Jonathan will write probably a very good article on it, and there are some interesting things that people said that Jonathan may quote. But to give you a very quick thing of what happened, I essentially gave this talk yesterday, but in 5 minutes. Okay, so I gave the headlines in 5 minutes, 10 minutes, and then we discussed, and you will see that in the article. I will send this patch, removing the comment in the sentence in the documentation. I will not go through it, but yeah, I prepared it. I didn't send it yet. I may tweak it a bit, but yeah, it's thanking essentially the many people we had already in the RFC, on the arena RFC. I had a list of people of 173. I think it says there 173 people. I think back then in the RFC, so almost 5 years ago, if I'm correct. Now the list is way longer. I cannot anymore try to make such a list because it's too many people, too many projects. I will miss people. So yeah, thanks a lot. So what now? How much time will we have more or less? Almost 20. Okay. So what now? This is what I personally expect that it will happen next year with certain probability, right? Certain confidence. So I hope we will not use any unstable features. Sorry, any unstable features by next year LPC. That's ambitious. It may or may not happen, but that's the goal. That's what we are going to try to do. And I mean language features. I don't mean compiler features. Compiler feature is another. It's another kind of worms, and there is many flags that we need, and we will need in the future flags that don't even exist yet in C compiler. So it's like that's a never-ending goal. But the language feature, we want to close that finally. Within a year, at most 2, I would say. Then I hope there is more progress in, as I said, for example, in free projection and other features that people is working on apps in Rust. Millions of users. I mean, there is a lot of users now in distributions, even if they don't realize or if the use case is not really very important, let's say. But yeah, when the ASMEM thing I mentioned hits phones and people start buying new phones, it's really in a few months, I think, as far as I understand, we will have very quickly millions and millions of users of Rust in the kernel. Again, Tira Nova, and all the GCC story that I told you. I think next year we are going to have the big news on both GCC Rust and the backend. So both projects apparently, I think they are going to reach a useful point at the same time. So that's amazing to see. And now a few things, until we have time, of things that will happen in the near future. Or one is upgrading the minimum version. As you know, we fixed the Rust version at some point, right? To Rust 1.78, and we kept it so far there. But I wanted to propose here, and if we get feedback, please talk to us if that works for you or not. My proposal is we will follow Debian's stable Rust version. So for example, Trixie, the current Debian stable, which was released this summer, has 1.85. Nowadays, we are at Rust 1.92, which is released, I think, today. Or yeah, today. It's Thursday. So the idea is, well, when Debian stable releases and a few months pass, then we bump to that version. Okay, I don't expect many people trying to build the kernel with essentially unsupported versions of the Rust compiler in very new kernels. Now, of course, that's still a smaller window than C. So we may want to go for 2 Debian stables in the future. So for example, we bump to the Debian stable when the next one releases, right? And so on. So that's my proposal. I think people in the Maintainer Summit also agreed it was fine for them for the moment. It may not be fine for enterprise distributions, but that's, I guess, the problem. And we can help, okay? I don't mean we don't want to help, but yeah, 2 Debians is the goal. In I don't know, 2 years time, for example, we can see we can do 2 Debians. Next, build system. So there is a new build system is essentially generalizing the build system that we have in certain ways, because we need some things in the build system that really need to be done now. We could wait until now. We could delay that change until now, but now is the time to do these build system changes. Because just to give you a quick summary, essentially the problem is that the Rust crates have dependencies, and there is a graph of crates, and there is no header, so you cannot just compile all the Rust code in parallel. So you have to put some dependencies between them, and Kbuild is not really meant for that. So I have been working on a prototype, and I will show you a few examples here very quickly. I plan to discuss this here in LPC with Kbuild and Nathan and Nicholas and KUnit as well, David, etc. To see if they're okay with it. And yes, putting it in the next cycle or 2, and then we have essentially a year until the next LTS to sort out any issues, and then the next LTS should have the new build system. In principle, you should not see many changes. Like, it's not really it doesn't change much. It may change how you declare modules a bit, but that's it. So how it looks is, for example, this. So in the prototype I have, if you have seen the documentation in rust.docs.kernel.org, you see documentation, but in the left side you only see, core and a few crates, essentially the kernel crate, right? With the prototype, we have all these crates at the left side, and you see all the things. So we will get all that. And importantly, you can have dependencies between those. So this is the graph how it looks today, except you see the top one there, which you cannot see. But the point is, I have another screenshot that zooms in. But the thing is, we have the kernel crate there, which is the middle, and then all these arrows go to the kernel crate, and that's essentially the flat model we have right now. Now, with the prototype, we can have things on top of that. So you see I have an example there, which is a crate there, a node in the top that is depending on that layer. That is what we cannot do today, right? What we cannot do today is put things on top. So we cannot have a graph on top of the kernel crate. We can have it on the bottom, but we cannot have it on the top. So zooming in, this is how it looks with the prototype and scene and other crates. This is essentially our graph, our dependencies today. And this is what I was mentioning before. You see there the Rust work queue. I created a new crate called work queue 2. I extracted from the kernel crate the work queue abstractions as an example, and then I created a sample module that depends on that. So is the Rust work queue sample depends on the work queue abstraction, which depends on the kernel crate. Okay, and the idea is later we will split things even more and more and more. And we extract the abstraction from the kernel crate, and we create a graph on the top. And that's what is needed, for example, soon for Nova, for example. As usual, I want to thank the sponsors and the industry support. All these companies and more gave me a statement support or have given financial support, etc., etc. So I want to thank you, all of them, very much. There is other companies as well. For example, NVIDIA is putting a lot, I mean, 6, 7, I don't know exactly how many engineers working on Nova. And that's amazing. I mean, that's great to see. So it's not just the ones that are here. I am trying to get a statement of support from NVIDIA to see if we can put them here next year. There are related upcoming LPC sessions. Sorry, what? Okay, thank you. So we have some related upcoming LPC sessions. Well, Vitalis is already was this morning before this one in another room, I think. Then we have tier following. So if you stay in this room, you will have tier, a very cool demo, I think. So please stay. The Rust MC tomorrow, which we have 6 talks, if I remember correctly, is going to be very interesting topics. So please, if you are interested, please join. And there will be more time for discussion. And we will try to make it this year very, very discussion focused, as micro conferences are supposed to be. Then we have the Rust for Linux office hours on Saturday. So if you want to discuss anything with us, you want to propose an agenda item, please let us know, and we'll put it there, and we chat and we discuss all these things. We will have the Rust experts in the kernel in the room, many of them, even remotely. So yeah, please go if you have any questions or any ideas. We may actually do something like develop a driver from scratch. So if you want, for example, to learn a bit how to develop a driver, or you want to do things like that, go there, and we can have some talk. And then Danilos, as I mentioned, who couldn't make the talk, but you can watch it probably in a week or two, hopefully. Then, as usual, I say how to contribute. Go to that link. Those are the two main links that I think are important to know about for people that want to contribute. And that's it. Thank you very much. So I thought we had less time. I have some extra content, but backup slides. We can go through it, and we can do questions depending on how things are going. Maybe we do with questions.
Hi. I was wondering, do you envision Rust moving also toward the bottom in the sense, besides device drivers, for example, what about memory managers? Do you envision that, or has there been any discussion about those?
So normally I have I think I don't have it in the backup slide, but normally I have an introduction slide where I mentioned that the Rust for Linux project is not just about drivers. It's what people think it's about, but it's not really only about drivers. That's, of course, the first target we have because it was the obvious one. But we also do, for example, other leaf modules like file systems. Those Rust is very interesting for file systems as well, and we have people that want to use it there. We also have things like core, like you're asking about core parts of the kernel. I mean, the QR code generator, for example, is such a the QR code generator is such a core part, right? It's not a device driver, it's in the core. The thing is, it's optional. So what we can do now is, add things, whether they are core or not, it doesn't matter, as long as they are optional, right? As long as you can turn them on in kconfig. You cannot make them unconditional. That's the only major restriction due to architecture support and other things, right? There are certain features that we limitations in when you're trying to enable config Rust, right? There is a long list or complex list, not so long, but it's complex of the depends on that you have to satisfy to be able to enable. And we try to go through them to lift those restrictions. For example, one that we will lift soon, and we had the patch for 1 year or something, is the run extract, right? If you enable run extract, then you cannot enable Rust. So I talked yesterday with Case, which was asking me, hey, what about the run extract? And I said, well, I had a patch there in the mailing list, and he took a look yesterday quickly, and he said, oh, yes, it works for me. So we will add it, and then we add the lift there, so we can remove that depends on, and therefore you have less and less restrictions. So over time, we will be relaxing those restrictions, and you will be able to use it for more core paths. Now, for the unconditional thing, that's in the future. Okay, I cannot say when we will get there. We will require more architecture support. We need the GCC Rust or the CodeGen, the backend, the Rusty CodeGen GCC to work very well so that we can do things unconditionally. When we get there, then yes, I think it could be unconditional. We could have things that are unconditional, but it will take time. I mean, I don't think we are there. We just finished the Rust experiment. Now we have to continue working. There is a lot of work to do, and the Rust experiment is not really the end or anything. It's just that we think the trade-offs are good enough for the kernel. It means that we prove that the Rust kernel is a net positive, not just technically, but also procedurally and socially and so on. So yeah, so I hope that clarifies a bit the question. Yeah. Thank you.
Oh yeah, on the list of Rust topics, there's also a Nova Birds of a Feather Saturday at
Okay.
3 o'clock.
Okay. Yeah, it's true. Because Anilo was not. I'm sorry. Yeah, I should have added. Yeah, so yeah, I would repeat in case it was not. So there is the Nova in I think Saturday you said, right? Or at the end, then we have a Nova Birds of Feather. So if you want to learn more about Nova and so on, please go there as well. Thank you. Sorry for forgetting. Anything else? One more, maybe? Okay, well, if everybody's shy, thanks a lot again. I hope this is the beginning of a lot of work, so thank you. Hey, how are you doing? Nice to meet you. Thank you. Thank you. I was like, well, why is he showing
And then it shows us about webcam. Yeah, Andreas is getting it. I mean, when we're starting out. Yeah, that's why it's also.
We usually do.
Because people are like looking once.
It's about time for the next.
What's going on over there? The best we could.
Microphone. This one you do.
Any special photos?
No. The photo thing is more for Mark.
I've covered the A and B box with the shirt.
Hello, hello. You hear me?
Not really visible from the audience, anyways.
Hello. So we just have a talk about the Rust, which is the most hot topic in the Linux kernel. Now let's make it more fun to mix Rust with a GPU driver. We have Alice and Daniel. We're going to talk about a new Rust GPU driver. Please.
All right, just a moment. Is this good? Can you hear me? All right, can I start? All right, so thanks everybody for being here. We'll be talking about Tier, which is the driver that Alice and I and other people have been working on for the past year and a half. It's a GPU kernel mode driver for ARM Mali GPUs. We're testing it on the G16, which is somewhat recent. We'll talk about, before we can go into the talk, we have to talk a little bit about how the graphics stacks on Linux works and how the how GPUs drivers are actually implemented. We'll talk a little bit about the API. We'll talk a little bit about what's implemented at the user space level versus what's implemented at the kernel level. We'll have to talk a little bit about CSF, which is the interface that ARM gives us for job submission. And then after that, Alice will be talking a little bit more about the abstractions, about the prototype, and also our future plans. All right, so starting with how a GPU works very briefly, because we don't have a lot of time. Basically, you start with the geometry. So what you're seeing here is basically a collection of points, and then the GPU knows how to draw lines between them. So what happens is you stash all these points into some buffer somewhere, and then you can start to generate some meshes like this one, like a simple cube, a torus. Can I get the next slide? Eventually, if you start increasing the amount of geometry, you can get like real life shapes, like a face. This is a face drawn in Blender, I think. Can I get the next one? And also Suzanne, which is the Blender mascot, so on and so forth. So you have to have the geometry. And then the next thing is textures. So the geometry is going to give it the shape, but then the textures is going to give it like the real world appearance of some sort of material. So for example, here you have the texture for a brick wall. And then if you apply that on top of the shape for a wall, now you have a brick wall drawn by the GPU. Can I get the next one? And then the last thing is shaders. So shaders are full-blown programs. You can do a lot with shaders, but they're usually, at least you have to basically use them to position things on the scene or do some effects, so on and so forth. But they're like programs running on the shader cores. Can I get the next one? So this is like the, oh, you can't read that. This is the shader from VK-Cube. So this is the vertex shader. It's a program running for each and every vertex in the geometry. This thing is basically doing some math, some matrix math in order to compute some physics for the lighting, and then rotating the cube on the screen because the cube is rotating. So all I want you guys to know here is it just looks like a C program, only that it's running on the GPU shader cores. Can I get the next one? And this is the fragment shader. So this one is running for each and every pixel, and this is a pass-through shader, meaning it's not doing anything. It's taking the value for a pixel from the preceding stages. But even if the shader is a pass-through shader like this one, you still have to have them, because for most APIs like Vulkan or OpenGL, you have to have at least one vertex shader and one fragment shader. So what I want to say with this brief introduction is everything inside of the GPU world is a buffer, and then it's the job of the driver stack to basically upload these buffers to somewhere where the GPU hardware can access them. So the vertex, the textures, the command streams, they're all buffers. So here I have some basic example for an application, let's say VK-Cube. So VK-Cube will take the geometry, take the textures, and take the shaders in order to render a cube, then pipe that through some API like Vulkan,
then the Vulkan driver will eventually ask the GPU driver to allocate some memory. It's going to push all this data into these buffers. You have something called a command buffer, which is where you set up all your pipeline in order to render. And this command buffer can like reference the other buffers that you have uploaded. So for example, inside of your command buffer, you can say, I want to draw something. And the vertex data is in this given buffer object. The texture data is in this buffer object. The machine code for the shader is in this other buffer object. And then you can reference all of that so that the GPU can later find all the data you've uploaded. Then you record these command buffers into some software queue like VKQ if you're using Vulkan. And then at this point, the Vulkan driver will have to talk to some underlying layer, which in this case, it's tier. Can I get the next one? So roughly in terms of how the code looks like, you have roughly, like, I'd say 80 to 90% is implemented at the user mode level. So for the RMali open source stack, that would be, for example, the stuff in Mesa, which includes PenVK, which is the Vulkan driver, the shader compilers, a lot of other stuff. So that's the majority of the code. And then I'd say roughly 10% is the kernel mode driver. And I say this because sometimes people don't really know what we're actually working on when we're working on tier. They think we're working on the whole thing, but we're actually only working on a smaller subset of what's needed in order to get the GPU working on the system. So the user mode driver, again, it's the piece of code that's taking the API calls. So by API calls, I mean like Vulkan, OpenGL, OpenCL, if you're doing compute, or not for Linux, but like if you were on other platforms like Metal, DirectX, et cetera, it has the shader compiler, and it can basically translate some higher level commands like I want to draw, I want to set the viewport, I want to set some scissor information, et cetera, has to translate all these commands into some lower level GPU specific instruction that the GPU hardware can understand. So that's the user mode driver. And then the kernel mode driver is here only to assist the user mode driver. So the kernel mode driver will be doing things that only the kernel can do, which is basically sharing all the resources, the GPU resources among multiple users. So things like sharing the memory and providing isolation so that one GPU context cannot touch another context and then steal data or screw the other context up, or doing the interface for job submission, or, well, you can do job submission from user space, but this is not implemented in Linux today for any driver. Doing dependency tracking, so making sure that if you submit a job, the preceding job, if it's a dependency for the current job, the preceding job has executed, for example. Synchronization, power management, so things that only the kernel is able to do because it requires more privileges. Debugging facilities, error recovery, and basically being the bridge between the user mode driver and the underlying GPU hardware. So for example, for memory isolation, I'm going to go through a few of these bullet points. So GPUs nowadays, they can enforce some memory isolation. This is used for a few things. And again, this is enforced at the IO MMU level. So it's basically the job of the kernel driver to make sure that you set up the IO MMU with the right mapping so that if another context tries to access the memory from a third context, it can't because it's not mapped on his version of the page tables. And the IO MMU will trap. So this is something that tier does, for example. Can I get the next one? Synchronization, so it's absolutely fundamental in the GPU world that you never block, or that you shouldn't block during submissions. So you submit a lot of things and then you build a dependency graph saying, I have this job depends on a series of previous jobs, which themselves depends on other jobs. You build a dependency graph and then you submit everything to the kernel. And then tier is the component that has to basically enforce that this dependency chain is actually being followed. That jobs do not start before the dependencies are done executing. Also, you have to basically tell user space when you're done, because user space can wait until some operations are done, usually sync objects, which is a DRM thing, which is basically a container for DMA fences. And if you wait on something that the driver never signals, if you're waiting on a sync object that the driver never signals, then you've just deadlocked. And it's the job of the driver to ensure that all fence operations execute within a finite amount of time. Otherwise, the computer would deadlock. So job submission, you can do job submission from user space, but again, this is not implemented today in Linux. Again, tier is the thing that's enforcing the dependency graph is actually followed. Can I get the next one? Error recovery, because if you're working on something and the GPU crashes, then that has killed everything on the system. It has killed GNOME, has killed your word processor, your browser, whatever it is that you were working on, that's going to be dead. And in particular, if you don't do it in a way that, well, if you get a fault and it's recoverable, then you should recover. If you get a fatal error and you cannot recover, you should reboot the GPU and start over from a clean slate. Because if you don't do that, then you have to reboot the machine. So it's up to the driver to ensure that this doesn't happen. Also, power management, again, it's up to the driver to know how many people are using the GPU hardware and make sure that if nobody's using it, if it's idle, you can have a lower clock, for example. Well, the GPU can work without this, but it's going to be using more power. And debug facilities, because when things break, the GPU driver is the only component that knows how to spew out something that you can use to debug. However, the kernel mode driver, again, the user mode driver is translating the API. So the API for the user mode driver is massive. It's as big as Vulkan or OpenGL or OpenCL, completely massive. But like the kernel mode driver is much slimmer. It's basically, there are two major components in the, can I get the next one? There are two major components in the black screen. In the kernel mode driver, and they're basically allocating memory. So BO create, BO mmap, which means I want to mmap this thing so that the GPU and the CPU can access the memory. The VM stuff, like VM create and VM bind, is used for letting user space decide what gets mapped where to what addresses. Again, this is related to the IOMMU thing we talked about earlier. And the group create stuff, group submit is just give user space a way to have access to the ring buffer in the GPU so that the user space can start submitting work. And in a nutshell, just so that we can move on from how a GPU driver works and what tier really is, this is what we have. We have a UAPI. We have basically memory management, which includes this VM thing in order to isolate processes, buffer object management. Then you have this gigantic thing doing the scheduling, meaning who can run at the moment, like which job, has its dependencies fulfilled and can run at this very moment. So there's a component inside a tier doing this logic for all the time. Like whenever a job completes, you have to figure out basically, okay, a job has completed. Does this job completing lets me run other jobs because this job was a dependency for other jobs, for example. And then below this, you have the hardware, right? You have the IOMMU, the firmware scheduler, and the video memory. And the cores, right? The shader and the tiler cores, et cetera, et cetera. Can I get the next one? And we have to briefly talk about CSF because tier is basically dealing with CSF. So in tier, we never really get to talk to the cores. You never really talk to the shader and tiler cores directly. You communicate with the microcontroller unit. And this microcontroller unit is doing everything on your behalf. So it gives you this shared memory region where you can place data in and out in order to control what the microcontroller is going to be doing. And then it gives you a ring buffer where you can place instructions. And then the microcontroller will be basically taking over from there on. So can I get the next slide? Again, we have to boot this microcontroller. And this is something that we cannot do at the moment upstream because we cannot allocate memory. Therefore, we cannot allocate the shared memory region that we need in order to talk to this microcontroller. So in the upstream kernel, we can basically only boot the driver. I'm not sure whether you can see this, but it starts all the way over to the left with the command buffers. So previously, I told you that you get command buffers, and you record these command buffers into a software queue, a VK queue. And then, well, it's a software queue. You have to back it up with some hardware thing, right? And then is where tier comes in. So tier will create in the CSF nomenclature something called a CSF group. And then this group can be placed in a hardware slot. And then once you place the group in a hardware slot, it will have access to the ring buffer. And then this, the microcontroller unit will basically start to schedule this buffer. I'm sorry, schedule this group into the actual hardware cores for execution. And then once the microcontroller sees that the hardware cores have finished the execution of a given workload, it will raise an interrupt. And then once these interrupts are raised, you can use these interrupts to let user space know that a given job has completed. All right, so much for that. Now that I've given this overview of what the driver really is, now Alice is the one who's going to be talking about the prototype and where we are with the abstraction. So,
hey everyone, does this work? Can you hear me? Okay, perfect. Before I begin, does anybody here have an HDMI cable? Okay. Anyways, yeah, next slide, please.
Okay.
Okay, so for the Rust abstractions, so you may know we have a lot of abstractions upstream. Here you can see the most important ones that are required by a GPU driver. At the top, we can see stuff like DRM, which is GPU specific, and some of that has already landed, as you can see. Then we get slightly more general. There's the clock and the regulator, and then there's IRQ, callbacks from interrupts. All of this is there, and we can even have like work queues, which have been in upstream for years in Rust because we also use them in other drivers, right? So, next slide, please. So, of course, for this, we still need some more abstractions. So we have a shared memory, and there's this thing called GPU VM, which is an abstraction for managing where objects are allocated in memory. And then there's the IO page table, which that basically creates the data structure that the GPU hardware uses to map from virtual to physical addresses. DMA fence and SIG objects, which are for synchronization, and the scheduler. So most of these are in progress, but not landed upstream yet. Okay, but that was upstream. What's more interesting is what's downstream. So downstream, using prototypes of all of these abstractions, we actually have enough that we can boot GNOME. We can, open a terminal. Here you can see a terminal with a bunch of logs from the driver. You can even open Firefox, watch YouTube on it. So yeah, you can do a lot of stuff. You can even play games on it. This is a screenshot from a game called Super Tux Kart, which, yeah, so next slide, please. Yeah, so I mean, all sorts of cool stuff. Yeah, and now we have it downstream, and it seems to be working. So how do we get upstream? Yeah, so how do we go from here? We have something sort of working downstream, but we want to get upstream. So, yeah, we have the prototype, but there's a bunch of shortcuts in that. We would like to, think about how can we take this thing we put together, which proves that it's possible, and how can we make it actually proper? And also another thing that's kind of interesting is that, yeah, Rust lets you make sure that a bunch of things are okay, but the question is, you can actually use unsafe Rust to add new custom checks to the language by designing APIs that enforce certain properties. And I think there are some very interesting cases where we might be able to design some APIs that enforce additional things that might not be something you always get with Rust. For example, like when the GPU accesses an address, I mean, from the kernel's perspective, it's just an integer. So you pass to the GPU over some register. But if you can build an interface on top of that that ensures that these integers are not, just attacker-controlled integers, maybe you can actually avoid some of the very common problems in GPU drivers. Yeah. So we have this prototype, and it's also serving as a test bed for many of these abstractions that we have these downstream versions. We've used them actually in a real driver to get some experience about, like, does this API actually work, or do we need to change it? And there have actually been some cases where we, for example, GPU VM, we learned some things about, we had to use unsafe in the driver in these places. And so I went and redesigned the API so that you no longer need unsafe in those places. So and there's also the job queue, which is an ongoing, there's all these APIs where actually using them in a real downstream driver is going to be very useful for actually figuring out if the API is right. Okay, so now we get to the fun part. So we want to do a live demo. And I don't know if it's, we can put it up there. The demo. Did you find an HDMI cable?
Take all the stuff from here and move it from
Can everybody just come over here and just look at the screen? Can you turn the screen around? What's that? No, it doesn't work. Oh, you found a cable? Yeah.
I just want to comment about the on the enforcing more safety, especially for typed register access. There's been a lot of work on that in the I believe it's like the Rust embedded group. They, especially for the STM32 class of microcontrollers, they have a tool that will compile from, I think it's called SVD files, which is something the manufacturer of the hardware provides, to Rust code. And then that provides, like, if you have a bit field that's only 3 bits shifted up somewhere in the middle of your register that can only assume certain values, you get all of that for free. So like if you have all of your GPU registers, you can maybe leverage some of that to get
yeah, so I mean that provides one level, right?
Sure.
So here you're going to have, this register fits 6 bits of data, and so you can only, you can't accidentally pass a larger integer that doesn't fit.
Yeah, exactly. That's
but
what
then
they
on
do.
top of that, right, the registers with these addresses, right, it's just a 64-bit integer. Can we do better and actually enforce that the integer points at real memory that it's okay for the GPU to access?
Yeah, I think you should check it out.
Yeah, sure. So I don't know what's happening up there. So while they're setting up the demo, I'm going to need some volunteers to play our racing game. So we need 2 people. You and you. So while they figure this out, can I take questions? Okay, there.
Thank you. Thanks for your work so far. Now, this may be a slightly misinformed question because I don't have all of the context on the tier driver, but I was wondering if this driver covers video acceleration and if there's plans for it. Because so far we've been talking about 3D pipelines, right?
About video acceleration?
Yeah, like hardware video encoding and decoding.
So my understanding is that those are just shaders you run on the GPU. So from the kernel mode driver, it's nothing special. But I could be wrong.
Yeah, I mean, I suppose you can implement it with GPU or with shaders. But I believe some Mali hardware have like video encoders as well. In any case, if that's not covered, it's fine.
I don't remember seeing anything like that in the C driver. So I assume that from the driver's perspective, it's just a shader using special instructions. But is it
Thank
not
you.
working?
I don't think it's gonna work.
Okay, well, in that case, yeah, let's take some more questions.
I guess technically it's two different parts of the kernel, right? Video acceleration will be taken care of by Video for Linux, which is a different driver and a different thing because it's different part of the hardware as well. You can also do it using GPU shaders, but you also have dedicated hardware. I think Daniel actually could answer that question, but he's focusing on something else. But how about the hardware acceleration part of a Mali? Not of a Mali, but of a chip. It's not taken care of by TR, right? It's a different thing. Like video decoding and encoding.
We managed to figure something out, so we're going to be recording the screen from a cell phone, and
Okay, I think we're ready.
Okay.
Okay, so what's your name? Wilfred and Shang. Our two players. All right.
Take the controller, I guess. Yeah. Oh, we had the slides with the key presses. All right, so go to split screen multiplayer.
Okay, so the button to the left is accelerate, right? And the bottom button is reverse. No, that's use key. That's use item, and the up item is reverse, and the
I think this one accelerates, this one breaks, this one kills the people in front of you with the items.
Okay.
And
okay.
the all right, so go to split screen multiplayer. Choose a card. Sorry, go back, please. B. All right. Yeah, I quit it, but we can restart it. This is so much fun. All right. So set it up. Plus select, please. And A. Select.
Oh, select A.
Choose a card.
Yeah, I want to choose.
A.
Why does it say GPU 0?
Huh?
Maybe the top counter is not working, but you can see the third number is the number of frames.
A goes forward, or maybe X. Oh.
Okay.
So you guys can see it, but like if you alt tab into demask into the terminal, there's a lot of prints from tier saying that it's mapped a bunch of things and it mapped things. So the driver is definitely working a lot. It's just this mango thing that we have to display the frames that I have no idea what it's showing. Yeah, that's what I just said. I have no idea why it says 0.
No.
It's either A or B or.
No.
Watch out.
Who's winning? Yeah. Yeah, this is only the downstream prototype. We can't do anything upstream yet. Just probes, basically. I was gonna say that you guys would be sure that this is tier if it deadlocked, which you may do eventually. I've had this experience before.
All right.
Who won?
Oh. I haven't looked like any items.
All right, guys. Thanks for playing. I don't think so. Alice, do you wanna?
Yeah. So, yeah, that's it. And yeah, I mean, we get pretty much the same performance as we do with the C driver. So
Yeah.
yeah.
We have the demo on the 4th floor. So if you guys want to play for real, like we're
yeah, we have a booth on the downstairs.
Yeah.
So if you want to play the game on the Rust GPU driver, you can.
not through a phone, but with the actual controller on this display.
Yeah, so come check it out.
Yeah.
And I think that's all. So thanks for coming.
Thanks for joining.
Big stuff. At least we showed one game.
Thanks so much. It was perfect. Thank you.
I had a question.
Yeah.
I had a question. So you mentioned that once you got the game to deadlock the driver. So how do you debug
Deadlocks?
Yes, because like, as you said, there are so many buffers involved. So how do you debug something?
Because well, if you deadlock and the kernel crashes, then most of the time that's not what happens. So the GPU will still be operational, and it's going to tell you, for example, I'm stuck. And then you have to add code in order to figure out, okay, there's a magic thing that the hardware is stuck. And you start probing from there, like, for example, what is the instruction? And you start to basically decompiling the instruction. Or, for example, are you waiting because somebody was working on something and this work never completed? Like, there's ways to do that. And basically, hardware is like very hard to work with.
Yeah.
So you have to. That's the only interface you have. Basically, trying to figure out dumb things from the hardware. Where it's broken.
So it's quite manual.
Yeah.
Provided by tiers.
At this very moment, no, because it's just a prototype, right? But for the C driver, which is the driver that people actually use, there's an infrastructure that all GPU drivers have in the kernel called DevCordon. Not a GPU thing, but it's also used on other GPUs. And they will collect a bunch of things which are vendor specific. So the AMD GPU guys know things to dump. LXC guys know what to dump, and etc. So they will dump all the information on your kernel driver and dump that. Because it is like access to the underlying hardware and the user mode driver design. And then you take all this information, dump all this, and then you send that as a dump file to so that user space can actually decode that. And then you can build your own tool. For example, NVIDIA, you can build their own tool saying, hey, this is what's broken. And then you can debug.
So this interface is something that the C counterpart does use.
The C driver has actually with ARM only, it's still work in progress.
Okay.
But for all other drivers like AMD, Go, they all have that.
Those guys use it. It's not a tier specific thing.
No.
Debugging is not a tier. Okay.
Like kernel drivers are the only ones who can control this debugging.
I think the no, from here. I second though.
Eyeballed it. Oh, and it says like it's 20.
Anyway, so at the moment, what is your object right now?
Thank you. Wrong with the HDMI cable. No, everything was working fine except for the cable, like the webcam that takes HDMI. Just the
Yeah.
But USB-C on this one is not. Can't compare it to anything.
Did what we said we would do.
You know, my
device
was
sounds
like does not have
oh,
the
let's
case
say
I usually don't. Where you destroy the network and that's it. Basically using it headless. So
Yeah. Let's just carry the whole thing. Oh,
right.
okay, I see.
Is that right?
Huh? Yeah.
Instead of lifetime. I think it's an issue. That way. Load like it's I want this like or on YouTube, I want this basically.
It was completely done on the spot. Like we had to, even the power wasn't really working.
No?
So, yeah, because we had to use this thing. Like this thing is from.
This is mine.
Okay. I could have guessed.
Can I have this one?
Lifetime of Excel.
All of this. All of this.
Thanks.
Also. power brick?
Yeah, that's mine.
And then thanks so much for that.
Sure. Yeah, so love this. So maybe next time we should try it ahead of time because we have an open source video conference system, not very featureful. Not so many users, so there are certain not being tested all the time.
So we tested a lot of things, like expecting to be given a link that this could happen, which is why we didn't.
Yeah, we have a very interesting way of present from your laptop. Everyone present from the cloud. Just you take over the click button from the cloud. So I would say it's a good model in some sense. If we get everything right.
I just wasn't expecting it, but it's good. I mean, next time I'll think about it.
Yeah, next time we tried it out earlier. So,
I think we did it in this lot. Thanks a lot for the help again. I appreciate it.
Honestly, Alice, I made them. Yeah, I checked afterwards. Apparently,
yeah.
Who does this for? I've seen Breno in like another.
He's proposed a micro conference. He's the lead of that.
Yeah, I mean, he was asking me if I want to have a call.
Right. So there's this is the main referee track. Other main track to get some other organization, and then we have the very long. Yeah.
One of you gets one, and I'll introduce and then hand it off to one of you. Nice bright red. Make it happen, yeah. Exactly.
And now I works. Is it time?
Okay, I think we're top of the hour, and I'm hoping everyone had a pretty good lunch. So I think we're going to get started. I'd like to introduce our next two speakers, Yuri and Gabriele. We'll be talking about RV and the deadline scheduler. And with that, I'll turn it over to them.
So, hi, we're going to introduce now our work on the runtime verificator on the deadline server scheduler. So we are trying to validate some of the specifications of the deadline scheduler and servers with the runtime verifier. So,
yeah, so this kind of, well, the format of our presentation is kind of an experiment. So we are essentially trying to replay what happened in practice between me and Gabriele. Of course, I'm going to be faking the initial part of this because I'm going to be saying I didn't know anything about RV, which is, of course, not real since I've been working with Daniel Bistro de Oliveira, that unfortunately is not with us anymore for several years. And of course, I wanted to say that he was the original author of all this, and so it's actually nice to see that this is still under very much development. So that said, again, faking the thing. So I was, I'm not sure if everybody knows me, but I'm maintaining this deadline scheduler, and I guess I always thought I wish I could validate it properly. But essentially trying to check that the implementation is adhering my mental model of what the scheduler needs to do. And so I started doing, yes, some research. And I don't know, I went to Wikipedia, say there is maybe some validation thing that I could use to validate my my implementation. Yes, I found this, well, that there is this thing called runtime verification. Well, it seems promising. Maybe there is something in the Linux kernel that actually is implementing this. Yes, I was lucky. So actually there is a runtime verification mechanism that seems to be, well, when I read the documentation, I thought, yeah, this seems pretty similar to what I had in mind. So let's see how who actually did this and who's maintaining it. And yes, that's how I found Gabriele. So I reached out to him. Of course, we work together, so it's kind of silly. But anyway, I reached out to him saying, do you think we can use the runtime verification thing to validate the sched deadline implementation? And essentially, I come up with my very high-level type of expectation from this exercise. And so I thought I have a mental model of how single deadline task should behave according to, well, theory and what's implemented. I would like to describe them a bit more formally than with like words, English words, and then possibly check that the mental model that I have actually adheres to what the implementation is doing. And so some ideas came up to mind. And so, for example, very simple things that came to mind was, I want to check the deadline tasks don't use more runtime than assigned. In Deadline, we have this runtime concept, and I want to check that tasks cannot exceed that. Another thing that, of course, I want to possibly check that tasks don't miss their deadlines, which, of course, nobody wants that to happen. And well, one recent thing that has been added to Linux is this concept of DL servers. So essentially using scheddeadline to service lower priority tasks if they need to run and they are in kind of struggling running because there are higher priority tasks. And essentially, I wanted also to check this with the model. So, okay. Reached out, and this was his initial reply.
I have it.
Okay.
Yeah. So now I'm going to pretend I don't know anything about the deadline scheduler, but Yuri told me what are the models that he would like to validate, and yes, we can validate those kind of models, and we're going to use a new thing actually that is timed automata to model those. So what are those? They are an extension of the deterministic automata. That is another model that is already present in RV. And essentially, it's a kind of a state machine where the current state and the event that is occurring determine the next state. So we're just moving around in states. Now, I'm talking about events. Those are just normally trace points in the kernel. So everything in here is something that runs in kernel space. So we're not talking about static analysis. We're not talking about some kind of analysis in user space. This is all kernel code. So we make them timed automata by adding constraints. So the constraints, in this case, they are general on environment variables, but in this case, the environment variable is a clock. So that's why we can call them timed automata. So there is also a special type of constraint that we see here. It's an actual action. It's a reset action to reset the clock. And basically, in this case, we can say that tasks, in this model you see here, tasks can stay in the running state only before their deadline. So after that, there will be a violation if they're still running. So what is actually a violation? What does it mean? There are three types of violations. The first one that you see here is actually the same thing that we can see in a normal deterministic automaton, when an event is not available in a state. So in here, you say that the state, the one that is marked in red, can't switch in, doesn't have an arrow for switch in. So if we do see that there is a switch in event, that is a violation. So something is going wrong. We are not reacting according to specification. Then the other two types are actually something introduced by the hybrid automata that is, let's say, timed automata and hybrid automata are roughly the same thing, where timed is just a special case of it. And if we have a constraint on an event, then when the transition happens, the constraint is checked. So in this case, if we have a sleep with the preemption count that is different from 0, that's a violation. We don't want that to happen. And just like we've seen before, it's also possible to have constraints in states. So in this case, if we don't leave the state running by the time that the deadline passed, so when clock passed the deadline, this is a violation. So we don't want that to happen. The model in this case is wrong. And we would react. We will see that later, what does it mean. So now we are talking about monitors, about states. There are actually instances of those monitors. So we're talking about, let's say, the running state and throttle state, those kind of things. This is another model. Those are states that belong to a task, for instance. So we will have actually different instances of this specific model per each task. This is an example. Actually, we can't only use tasks because since we want to validate also deadline servers kind of behave like deadline tasks, but they're not real tasks. So in this case, we would need to follow scheduler entities, so deadline entities that are some kind of other object. So this would be a bit more complicated. So in the example here, you see that's a very simple model. The real model is actually a bit more complicated, and is showing through all those errors that a task or a deadline server can stay in the running state only as long as it has runtime. Once it doesn't have runtime anymore, then we need to go to throttle or to preempt it. It cannot be running.
Okay, yes, that sounds interesting. Although I think we probably need to add new trace points to the kernel, because I don't think with the essential trace points and the kind of information we can extract today, we can actually essentially model and have all those transition from one state and another state. So I would probably, I'm thinking we should add an event for throttle, trace points for throttle events. So essentially that triggers when deadline entities depletes their runtime. Maybe one for replenish events when essentially the runtime is replenished. There is a tick that is firing and the runtime is replenished. And most probably also for the deadline server thing, we want to track start and stop of the server. Maybe it's enough for now. What do you think?
Yeah, that's probably enough. Let's see, actually, here is a patch that shows how we can work through it. We submitted it. There are actually 4 things that we are introducing in this patch. The hybrid automata, of which the timed automata are actually just a special case where the variables are clocked. Then there are per object monitors, because currently we can just have per task monitors, but in this case we need to follow deadline entities. So we need a bit more of a configuration for that. Then there are the trace points that you just mentioned, and a couple of models to represent the throttle relationship and not tasks for not to miss their deadline. So those that actually I shown a bit earlier. So actually this I shown before some of those models. This is how it got after a bit, because the first model was a bit more simple. It didn't really work for deadline servers. So in here, actually, this is how it became after. So it extended a bit, and there are a couple more states to represent. For instance, the server is sometimes running, but sometimes fair tasks are running while the server is not running. It's not boosting them. So in this case, we need a few more states to represent that, while real tasks, deadline tasks, don't really have those kind of states.
Okay, that's very good. So the only problem now that we have is that I realized that, as I said, the DL server is still very new, and it's always changing because we find issues with it. So it's actually not really like I was describing it, I mentioned to you in our first conversation. So do you think the model is still valid? So here, well, I won't go into details because we don't have time, and I don't think we want to focus on deadline. This is really about the runtime verification thing. But those are 2 examples of pretty big changes that happened to the DL server while we were working on this thing. And so, yeah, so how do you think we should deal with this? And maybe, I guess the nice thing is that if the model can somewhat adapt, then maybe then we can use the model again to validate the new, let's say, the new behavior of the DL server.
Okay. Yeah, actually, the model needed to be adapted, so we can adapt it. But after doing that, we still see that there are some things that I'm not really sure they are expected. So, like in this case, the model is seeing that some tasks are still, well, the server are still boosting tasks after their deadline. So after the deadline passes, this is something that is expected. So we see something like this. This is a trace from the system, and we see this is just extracted. We see that the task in here, well, the server in here is getting replenished. So it means that here is getting new runtime. And typically the deadline, in this case, the default deadline is after 1 second. Then we see here the switch in, so it gets to running. This means that it's boosting a task. The server is boosting a fair task. But this thing happens a while after. It happens 5.7 seconds after the first replenish. So a bit shortly after, we see an error in the trace. This is a trace point in RV, actually, that is showing that this thing shouldn't happen. It shows that there is another event. In this case, there is a throttle, and that throttle is happening once the clock is 4.7 seconds after. So this is a violation. So is it something that really should happen in this case?
Yes, that sounds fishy, and I believe that the model actually caused something that it doesn't look really right. So yeah, it's working. Well, the model is working. The code is not really working, but I guess that proves the point that by using this approach, you can essentially again model what you expect from your code and actually verify at runtime that it's actually doing what you expect it from the model. And if it doesn't, it actually tells you, look, there is something wrong, and then you come up with a fix for it. Again, not going to detail, and please reach out afterwards if you are interested into it. But as I guess as one result of this interaction, and also thanks to Peter Zeiser, of course, we fixed a few things in the DL server upstream, which were actual problems. And those are just two examples. So this essentially went through how it actually works in practice between us. So I'm not sure, maybe we want to conclude with a general question, and also for, I guess the audience might be interesting to see how to do this, how to deal with this. So what's the magic recipe? If you think you want to model your own subsystem and your own thing in the kernel, how would you possibly do that?
Yes, so let's go through the steps, how to create a new model in RV that can be for any subsystem. So in general, we start, of course, from an idea. So an idea of a specification that we know must be true, or at least it must be true anytime a configuration is correct. So if this thing is always valid, then we can model it and try as a monitor. So the idea, as we kind of seen before, it needs to be something abstract, theoretical, not too implementation dependent, because otherwise, if the code changes, then this thing is going to be broken very soon. So you need to have something like we said before, like deadline tasks cannot miss their deadline. So this is something that we want to work no matter how we implement the code. So it's a theoretical, let's say, more abstract idea. So we can model it right now. So there are three classes of models. We have seen two earlier. So the first is deterministic automaton. As we've seen, it's just a state machine where the next state depends only on the current state and the event. And in this case, it's represented as a dot graph that, whatever, is just a representation, textual representation that can be rendered to this picture. Then there is another type of model that is a linear temporal logic. We didn't discuss it here. This is sometimes more flexible to represent some things. So you can factor out some concepts from the main rule and make it more compact. So sometimes this can be useful to represent some different models. And the representation is just textual for following this grammar. And then there is the hybrid or timed automata that we have seen before. They're just based on the deterministic automata, but we add constraints. In this case, those can be also real-time constraints, but can be any general constraints, as we've seen, preemption count or something like that. Now, usually you have a choice in this. You can see if you want to have a deterministic automaton, linear temporal logic, or the other one. So, well, if you need to represent real time, then right now just the timed automata work. But then after this, you need to understand what kind of model you're talking about. And here you don't really have choice based on what idea you had. You need to pick how many instances of the model you need. So for instance, the easy way how to understand this is to understand what the states apply to, for instance. So if we have just one state in the entire system, so let's say the system is booting or it's running, whatever, then we will have a global monitor. So just one monitor for the entire system. If we have some kind of states that represent each CPU, so let's say the preemption count, this would be a per CPU monitor. Same thing for per task monitors. So we have the state of the tasks. And so we will have one instance of the monitor per task, so running tasks or whatever. And we can have actually something more complicated if we need to follow some different object. So we have also per object monitors. Those are a bit trickier, a bit more complicated to configure, but they can be used, as we have seen, for deadline entities. Now we can make our hands dirty finally and actually write down the model. So depending on what model type, model class we chose, we can just check the models, examples in the kernel tree. So there are plenty of examples in that folder. Or we can start directly if, for instance, if we have a deterministic automaton, there is this nice tool, the Supremic IDE, that we're using sometimes that would just generate these, you can export what you create in there into this dot representation. So that code is the dot representation. And that can be rendered and can be fed into RV. So right now we need to understand also how this thing applies to the kernel. So we found that there are some events and we need to map those to existing kernel events or non-existing. So typically we might find some existing ones like the switch events exist as a trace point. So for instance, the trace point shed switch can be mapped for two events. So it is a switch in for the previous task, for the next task, and a switch out for the previous task. Or we may use the other arguments, for instance, the previous state, to understand what type of switch that is. But in other cases, like we've seen before, the event is just not there. So we need to create a new event like the replenish. In this case, we need to be careful to get what we need from the call site. So in this case, we need the deadline entity. We may need the CPU because it's not easily accessible outside. So we need to pass them to the trace point. And now there is a script, rvgen it's called, that is in the kernel tree that we can feed the model that we just created, and this will just create files, so the C files, the representation that we can plug into the kernel. Here there is a lot of output because it tells you what to do to plug these files into the kernel to build it. This thing can be actually automated with the -a flag, and so it just plugs everything in, modifies the files and stuff like that. And this is actually not done because the rvgen script is actually generating these kind of stubs. So for things that need to be completed, like trace points, it would generate one handler per event. But it doesn't know that, for instance, some events share the same trace point. So we can just change them, add the right trace point, and we will complete the code in that way. Or likewise, if we have hybrid automata that are reading some kind of environment variable, let's say from the system, like the preemption count, we will just need to read it. Here there is a -1 because here we are in trace point context, and currently trace point have preemption disabled. So we just need to subtract it by 1 as an example. So finally, we can test the monitor. So we just build it and we can boot the kernel with the monitor inside. Right now, the monitors are part of the kernel. They're not as a module, although that can be done in the future. And the simplest way how to test the monitor is to use reactors. So reactors are kind of actions that happen when there is a violation in the model. So there is this RV user space tool that just launches the monitor, instructs it to have the reactor, in this case print K. So whenever there is a violation, you will see it on the dmessage. Or another very simple way how to validate those things is to use the trace points. So we can enable the monitor with this tracefs command, whatever, and then the trace points are actually available for any tool that can process trace points. So we can use trace CMD. That's actually what I used for the trace that I showed before. So we can select also other events that are relevant to the monitor and just have them in the trace. Or even we can use perf just to count events. Everything is allowed because they are trace points, so a lot of tools can process them. And finally, that's something that is a process that goes over again, because most likely the first time the model will not be correct, especially for complex model. Maybe you're just missing a transition, so some things don't work, but while seeing the trace, you see that the transition was actually correct. So you need to modify the model and just start again. But sometimes you might see that there is a trace that is correct, the model is correct, but that thing should not happen. So, or you think it should not happen. So it's a good thing to discuss upstream with the maintainers of the subsystem if this is an actual bug. And whenever you're ready with a monitor or whatever, if you have troubles and you want to discuss, there is a tracing mailing list you can just send around and we can see what to do with it. So what's next? This thing is not terminated, of course. We discussed a bit those future steps this morning in the presentation in the micro conference for the scheduler RT. And the natural solution is, continuation is to try to model all the the deadline servers, because right now we are assuming there is just one deadline server per CPU. That's no longer the case. There are going to be a bit of changes. So this, as Yuri mentioned, the deadline scheduler is a kind of a moving target. It's changing rapidly. So there are things that need to be adapted in this case. But also we would like to validate more subsystems. So it would be ideal to validate the functionality, well, on a functional level or even as a timing requirement of some other subsystem or other schedulers. There's a question. Where is the box? See the throwing skills. Wow. Yes.
So I know you pointed out that deadline scheduler is a moving target.
Yeah.
But wouldn't it be a bit more useful if RV could say, even though the deadline scheduler is moving, it's meeting its core requirements or core functionality?
That's the idea, actually. We are trying to, let's say, crystallize on an idea that is, let's say, the correct approach. Sometimes, since it's not that clear what the correct approach is, then the models need to be updated. But sometimes, indeed, when we...
What does correct approach mean?
Let's say there are some cases that we're not entirely sure if the server should boost a task or if it shouldn't. So it's not clear what is the correct behavior that the server should have. Is that what you're asking? If the
in part. So I think what I'm not sure about is once you have a model,
yes,
does it need to keep changing because the kernel has changed? Or can it be independent of the kernel? And so as the kernel changes, the model can then verify that core functionality has not been broken.
That's the ideal thing. It should never change. So yes, if a model is proper and the code under also is not changing, because especially some trace points, some events themselves had to change sometimes. So there was like, there are events for start and stop at a certain point. For instance, there was a stop that was like a light stop, and now that event is not there anymore. So some things really were changed at a certain point, but ideally, yes, we should have the model, and that should not change because that's the abstract idea.
And also, it's also maybe a trade-off. So how much, I guess, particular you make the model or general, you might need to, well, if it's very particular and modeling like a very specific thing, it might need to change because that thing wasn't like general enough. But if more than the model in general, it's less subject to changes. So also the kind of trade-off, I think.
Yeah, pretty much. Did it answer your question?
Partially. I think you and I are going to talk about it more.
Yes, yes, we can discuss. So, well, also another thing that could be useful is that right now we have just those three types of models. They might not be enough for every kind of specification we want to write, so it might be also possible to extend it further in case there are other requirements. So for instance, those timed automata don't support concurrency because all events actually are supposed to happen, let's say, serialized.
So
yes.
I had another question. You just kind of, sure. So if I have a specification, you know, I don't know, I'm just picking one out of so maybe the TDIS specification, for example, where, you know, it's come out through some committee. Is it possible to convert that into a FSM, a finite state machine, that can then be used as input here?
So what specification?
Any specification, maybe say TDISP, for example. How do you secure your link from the device to a confidential VM?
Well, I'm not familiar with that one specifically, but probably yes.
But I mean, you have a specification, right? It says you have
yes.
X, Y, Z, this is the state transition.
Then probably yes.
And then can we like find a way to maybe generate a FSM that can then be an input to this?
Ideally, as long as you can have events to move through that state machine, then yes, everything is possible. So if you can really have it as a state machine, or as well, like there is this LTL that is another type of specification, you can model it in that way as well. So it depends, of course, on the specification, but typically, yes, it's possible.
Well, if you think about it, also the constant bandwidth server, which is implemented by scheduling, it's essentially a specification of how the algorithm should work, and that's what essentially was modeled. So, yeah. Question? Yeah.
Like, how do you store the specification? Like, how is it fit to the system? And do you think it's worthwhile to make it depend on the kernel version so that you can have one specification for that kernel version and another specification for another kernel version, so you can keep, like, at least for LTS, maybe this can be used for regression testing and this kind of.
Yes, that's a good question. Actually, right now the specifications are in tree. So you make the model, as I've shown. You make the dot model, let's say, you convert it to whatever it is, and you have the code. Then you would commit that code to the tree, and then that stays for that specific version. It's up to you to backport it or not. And if you backport it and see that actually earlier on in another version it was different, then you have to change it. Or likewise, if the kernel evolves from it, then you might need to change the model for the future versions, but you can keep the same model for previous versions.
I mean, I don't think like the purist in me doesn't like the idea of a model being linked to a kernel version, because the whole idea behind the model is, hey, as I make changes, I verify it's not breaking. And if I change the model to match the kernel, I now have to verify the new model as well.
Yeah, but the reality is that distro ships like, I mean, you need to have a user space tool probably to run these and capture them. Maybe not, I don't know. And you need to ship this model somehow. So like, I mean, if you have, how do you ensure that the model is for the correct kernel version? So if you don't have that knowledge, maybe you're missing, because when you think about distributing these, I think you can have a mismatch between the two.
Because, sorry, Steve, a moment. So it's right. I actually agree with him. He's saying that a proper model, let's say, should be as abstract that the kernel should not move away from it. Yes, in reality, that doesn't always happen. So I agree with that as well. But maybe the model is not correct, or is not really what you want to model sometimes. Also, of course.
Yeah, I mean, that's exactly basically what I was going to state, was to make it more, you might want the model to be more abstract, just to cover the requirements of what you want to make sure you achieve. So it's more abstract to achieve and not really implementation specific, but sometimes it's kind of hard to do, especially with, like I said, the trace points might move around where you can't. Yeah. But if you're able to get the trace points in the spots proper, I think that's the ideal thing. Whether or not we could get there.
But then, you know, what you have
But then what you have to keep in mind is when you've changed the model, you now also have to verify the model works. Yeah. That's an additional step that has to be kept in mind.
All right.
Keep in mind, like, we added new features. Like on the fair, for instance, we had uclamp being added. This changed the behavior intentionally. So we need to rely on this being actually being configured. Is it enabled or not? And if it's enabled, like, so the behavior maybe need to cater for these changes. I don't think the scheduler behavior is supposed to be constant. So like, it should change, maybe not often, but I think it will change by design.
Yeah, as well, like it happened for the deadline server. It's not always clear when it should stop. So that's why if you're modeling when it should stop, and then it changes the rules for when it should stop, then of course you're going to change that.
So it's usually not a monolithic model. It's like a composition of smaller models. So maybe some of them are abstract enough that it stays as is forever, and some other bits might change. So that's also the same.
I think where I find this really, really interesting is when you start bringing in device models, which come through like an external specification that should not change very often.
Yes, exactly.
That would be interesting.
I had a specific question on the environment variables that you were talking about. So I think you were using time, right? Mm-hmm. You had a clock, and I understand that with trace points you already get timestamps in there. If I've got some other environment variable, let's say a global variable that's updated in interrupt context, and I don't want to have interrupt edges from every node, how do I have to update all of my trace points to now expose that environment variable, or is there another way of exposing it? I wasn't quite sure how that worked.
Well, it depends on what variable you're talking about, some of those things are global in the kernel, so you don't need to export them like the preemption count. You can just read it.
Just go in and get it. Okay.
But yeah, if it's really something that is not accessible and you really cannot access it without passing it to a trace point, then yes, you will probably need to export it.
Okay, thanks.
There's also dynamic trace points. I mean, you could actually, if there's a variable, you could say, hey, put this, within a function or a stack. You could actually, there's ways to get to it through dynamic trace.
All right. Yes, it's
last one.
Yeah, there is a thanks slide. I can put that.
Is there a good way to feed events into the thing that are not from trace points? So for instance, in a device situation where you're developing the device, you need to feed events that are occurring in the hardware into it so you can do co-simulation and validate the model as you're going along.
So if I understand correctly, this is something that through a driver perhaps you are handling?
Yeah, Linux looks at it as a driver perspective, right? But we look at it as a whole system. So,
yes.
Right.
Because well, you need to feed them from the kernel perspective.
Right.
So perhaps there is a driver that can react at that point, I don't know, an interrupt, and then you can fire trace points or anything from there. But it has to be an event in the kernel. It could be kprobes if you don't want to have a trace point, but anyway, it needs to be kernel code.
Right.
Does it fit what you're thinking?
Almost.
Okay, almost.
Yeah, let me think about it.
Yeah, we can talk offline if you have questions.
Anyone in the back?
Yeah.
Well, I guess maybe one thing to add is that don't feel intimidated if you think you might want to try to use this, but it might be intimidating because there is lots of steps to went through. Reach out, I guess, to Gabriele. He knows way more than I do, and I guess we are here to help. The idea with this is to try to, I guess, present to a wider audience and get traction, and maybe more people will start using it.
I do think, though, that for historical purposes, there's been sort of mentioned already, is we need some way of tagging the model against a version of the code base and keeping things tracked coherently together.
Mm-hmm.
Otherwise, when we're going back to LTSs and going back to fixing issues, we're going to cause it will run into issues. It'll run into problems, especially if you want to use it for validating something from 10 years ago.
Yeah, currently it's like automatic because it's really with the tree, so that happens automatically. But if we start to have them, I don't know, as PPF or as models, then yes, if it's separated, it should be tracked.
I mean, the question just for people in remote is overhead of trace points. So actually, if you're going to record into the ring buffer, there's actually a trace point benchmark that does it. It averages about 150 nanoseconds per event, but there's a slow path that when it transfers, that's if it's recording to the trace point. Now, that's overhead of a trace point being traced. RV doesn't use the ring buffer. It's just a function. It's actually, what we have is, so a trace point uses static branch to be enabled. So it's not even an if statement. It's just a jump to the train point code. And if you only attach a single callback, because trace points could have multiple callbacks. But if we attach a single callback, we use something called a static call, which is a direct call. It'll do a call. It doesn't even do like an indirect jump, because indirect jumps could have like the Spectre mitigation on that. So it actually modifies the kernel to jump straight to it. So basically, I guess the overhead is when you hit it, you're just going to do a jump or a call right to the RV code, which does the real quick. So I don't know, did you ever do any full benchmark on?
I did. It's very hard to compare them though, because there are a few types of model types or model classes, let's say. For deterministic automata, that's probably the lightest because it's really just picking the next state. There's not much to do. The other two types have a bit more logic into it. So it's also like dependent on which kind of event you're careful about. So I'm not entirely sure like the duration of it. I never profiled like as nanoseconds
And
or stuff
but
like
I would
that.
say that the RV code, I'm assuming, from at least from what I looked at, would be less complex than writing into a ring buffer. If the ring buffer, when the full trace event of a ring buffer is only 150 nanoseconds, I'm going to say that you're under 100 nanoseconds per easily. Well, and then cache, yeah, you'll have caches. Obviously, that's just kind of like, there's times where I hit, almost a millisecond just because it hit the bus thing and,
How do you verify that you have put enough trace points or in the right places? For example, to give you an example, so let's assume that you want to monitor a certain register to be not overwritten. You should identify different functions in the kernel that can write to that address and accordingly attach trace point that monitor these to not be accessed, for example. But if you miss a function, then you miss that event. Effectively. So,
There is probably a better way than trace points, right?
No, actually, Masami Hiramatsu has added something just, I don't know if it went into this kernel, it might just been here, but it's like hardware trace event, where you can actually put in a trace point that will trigger if you modify a memory location. Yeah, so I'm saying you use an example like weapons you call function. So if you want to know, like, or you just like, if you're looking at like, is this being hit? You actually could use something and say, if this gets hit, well, either like function trace or either function tracing or whatever, or kprobe will do a function. But if you're worried about memory locations, Masami just added it to 619. I think it got into 619. I did it. Oh, there he is. I was like, I was looking for you. I didn't see you. Here, you could talk more about it. Just real quick.
So that double probe, using that name for that hardware breakpoint thing, and it will be it actually missed that 19th window, so that I will put that 612, yeah.
But actually, that's a valid point, not only for memory addresses, because yes, let's say you have a needress shed event that happened, especially for that one, that this event is not always going through the same call. So you need to probably identify multiple calls where the same event is happening. And if you miss one, yes, then you're probably your model, although the model is correct, then the monitor will not work because the trace point is not catching all the time that the event is firing. So yes, you need to be careful about it.
Basically, how do you verify that the analysis is complete?
Actually, if you think about it, you have kind of your own requirements that you need. So you have to make sure you just match the model with your requirements. So are the requirements complete? If the requirements aren't complete, the model won't be complete. So you basically just match the model with the requirements to make sure that it covers everything. Right?
Yes, but in that case, like, yes, you need to trust that one of the two things is correct. So if you think that the model is correct and there are violations, that maybe you didn't put the trace points in the right places, or vice versa, you did put them and then the model is not correct. But yes, there is a kind of a dependency between the two.
3 minutes left.
Okay.
Right.
Thank you.
Thank you.
Yeah, go down.
Hello, testing. Okay, that's probably good. Testing, 1, 2, 3. Good.
Okay, we're going to restart now with our next session. Alexa's going to be talking about path safety, quote unquote, in the trenches, and take it away.
Okay. All right. Thank you so much. Yeah, this will be less of a, let's say, kernelish talk, but there's a lot of kernel infrastructure that went into what I'm going to be talking about. So I am, in addition to using kernel work, I'm also the maintainer of runC, which is probably the most widely used container runtime out there. And it's, the reference implementation of the spec and so on and so on. And for those of you who do run container workloads, you may have noticed we had some security issues last month, which were very fun to deal with. And that's basically what this talk is going to be about is, I guess, the history behind these kinds of issues, because they're not the first of their kind. And also because we, I guess there was a lot of interesting barriers and things we ran into. Even though I've been working on this field for quite a long time, we still ran into a lot of issues. So for those who are just not aware, the very boring diagram of where runC sits, effectively, if you think Kubernetes or most of the Podman stuff in Docker, runC sits in the middle for the most part. So runC is a OCI spec, so it has this specification. So the way you configure it is that it takes a config.json and it has this configuration format, and this will come important in a bit. But yeah, and you can specify effectively any kind of latest kernel feature that has to do with containerization. So you can specify UIDs and what capabilities it has. You can specify these sorts of things, and it's very, I guess, it's kind of plain Jane. Like effectively, it's like for each kernel feature, we have a field that says, I want this, I want this, I want this. That's basically all it boils down to, plus some stuff about how the lifecycle of a container works. And then you just run the container like that. And I mean, that's all the higher level runtimes are basically just doing that. It's not anything particularly special. And yeah, so when I say path safety, what am I talking about? So I'm going to be less helpful by splitting it into two more terms. So there's what I call regular path safety and what I call strict path safety, which is particularly important when it comes to procfs. So both of these are very important for runC, and the security issues we had most recently, they are very related to these particular problems. So when I say regular path safety, this is probably the most, I'm pretty sure this kind of security issue has existed since time immemorial. Like it probably existed in Unix, it probably predated Unix, where you have some path, you're opening it or you're operating on it, and some other process swaps out one of the components from underneath you, either with a symlink or moves it and so on. This is like classic check time use attack. So even if you check that the path is safe, you still end up accessing the wrong path. And so like and almost all of these are related to either incorrectly dealing with this was going to say legacy, mature program like run C, it's difficult because the whole program was written using this here's this path I want to write, here's this thing I want to write to, and you need to rework a lot of the program in order to get it to use file descriptors instead, which is the more modern style on Linux. And yeah, so this is like the classic example of code that you really shouldn't write, and the thing is that standard libraries and languages try to push you towards writing code like this. So it's not just C, and I mean in Go, only very recently did they started trying to work on this problem. For a very long time in Go, like the entire standard library was path-based. So if you ever wanted to just write like a normal program that writes to a file, it would push you towards writing stuff like this, where you are writing to /rootfs/ something. And obviously if rootfs is the root of a container, there might be some process running in that's malicious that is swapping files around, and they can easily trick you into accessing the host. Because again, we're talking about in the context of run C, where we are a host program, we're going to be accessing the whole host file system, and we're often running as root. So yeah, now OpenR2 gives you, for opening, it gives you all the tools you need. Effectively, you can just use open how like this. You specify I want to resolve in root. You open the rootfs, and then also I should use the pointer. Yes, you open the rootfs, and then you say, okay, I want to resolve inside the root, and then you set flags and you open it. Very trivial to follow. That's fine for opening, but opening is just one of the many operations you need to do. For more complicated things, you need to be a little bit more careful. In particular, the example here I have is making a directory. So you can't one-shot open a directory anymore. You now need to open the rootfs, then you need to open the parent directory of the rootfs, and then you need to make direct at the final component. And because this final component doesn't have any slashes in it, you can be sure that there's not going to be a race condition, because make direct does not follow trailing symlinks. So what this means is that for every single file system operation you want to do, you need to double check whether or not that it will follow trailing symlinks, or if there's a way to turn that off. And then you need to do this kind of dance, and it's even more fun when you have to do unlinking and stuff like that. So, but it is at least theoretically doable with OpenR2. Now, for older kernels, now OpenR2 was added a long time ago. I mean, it's 2019, so for basically any modern system already has it. But unfortunately, it's often blocked with seccomp because it uses pointers as part of the structure. As you can see here, it takes a pointer, which is not yet supported by seccomp. So yeah, so effectively, the old school way of doing this problem was that instead of using some kernel functionality, you would implement the lookup yourself in user space, and you would walk each component with OpenAT, and then you would have to, if you hit a symlink, you then have to read link the symlink, and then you need to figure out how you would walk from there, and so on and so on. And it's quite finicky to do. I've had to write that code quite a few times, as I'm sure many of you have, but you can do it. Note here, of course, is that all the rest of your code still needs to be file descriptor based, because you're going to run into issues otherwise. And usually, at least in the case of the most code I write, you end up having to do verification through proxyfd when checking to make sure that you haven't walked out of the root accidentally, such as when you're walking into ... and stuff like that. And this code's been replicated in lots of places. Systemd has chasad, which does this. Go, as I mentioned, they recently added support for this OS root idea, where you can effectively try to do this chroot stuff I was talking about in the standard library. And then you have libpathrs. What is libpathrs? So not to plug my own wares, but libpathrs is a Rust library that I wrote, which effectively provides a lot of helpers to make this a lot easier for user space. And it's built on top of OpenR2, and as well as having the fallback for OPath, as well as a lot of other hardening work that I've spoken about at other conferences, so I won't go into here, but that's the primary reason, is because it really takes a lot of work to get something that actually works properly, even though all the bits are there. You have to, as usually in the case with Linux, you have to build your own Lego set. And yeah, you can use with Go and Python and basically any language that has CFI support. There is a funny thing, which is that because let's say this year was quite rushed for me because we had all these security issues I was working through. We had to create this thing called Pathrs Lite, which is a Go port of libpathrs, which is a pure Go port, because when we had the security update, we needed to make sure that you can actually build without changing a toolchain, which led to a very funny situation, because the original libpathrs was written in Go, and then I rewrote it in Rust. And now we have Pathrs Lite, which is rewritten from Rust to Go. So we have code that went from Go to Rust to Go, which seems like a bit of a waste of energy, but hey, that's the way it turned out. And then yeah, this is just an example how you use it. It looks kind of similar to the first example, except everything has Pathrs in the name. And then you can open a root, and then you can create stuff in the root, and so on. And it's, unfortunately, it has the underscore thing that C is famous for, but it is at least easier than the alternative of using OpenR2 directly. So that's all pretty obvious and pretty, I'm sure that all of you have already heard all that before. The really fun thing we had to deal with was actually strict path safety. So in the case of regular path safety, usually you don't actually care what file you open, right? Because as long as the file is inside the rootfs, it doesn't matter to you whether you opened a file that an attacker moved from here to there or whatever, because the attacker, we assume, has access to modify any of the files in the rootfs. So if you open a file that has the contents you weren't expecting, it's not the end of the world as long as it's inside the rootfs. That's what the regular path safety is protecting against that. That's actually not enough because for certain pseudo file systems, it's very important that we operate on the exact path we expected. And procfs is actually the most critical of these. And I'll give you an example in a second, but yeah, the core issue is that if you have an overmount, so in other words, you have something mounted on top of procfs, or if you have fake mounts, so you have like a tempfs mount that looks like procfs, or if you have bind mounts or other things, you end up with either you end up not doing what you expect, you end up crashing the system, or you end up getting exploited. And this is examples that we did in run C. So if you want to set LSM labels, you have to go through procfs, through proc_exec. If you want to set any sysctls, you have to do it through procsys. And then if you want to reopen file descriptors, which is a fairly useful feature in Linux, you have to go through that. And obviously, if you want to re-exec yourself, you need to go through proc_exec. And obviously, in each one of these, if any of them were a bind mount, you would be screwed because you would open the wrong thing, and it's not entirely obvious how you would detect it. There are actually worse CVs related to this, a bit fewer than the previous slide. But these issues have been around for quite a long time, though it seems they're not actually that well known. But yeah, so an example of how you can do fixed strict path safety is actually, it turns out that for regular files, it's actually already solved if you use OpenAT2, because we have this resolve no xdev feature, which lets you block mount point crossings. So effectively, even if self-add or exec, any of them were bind mounts, you would get an error rather than opening the file accidentally. And if you do, now I excluded some verification work you have to do, which is that you have to check that proc is actually the root of a procfs. But because proc has a well-known root inode, so the root inode of procfs is always 1, and you can check that the file system type is proc supermagic, you can be sure that you've gone from proc to there and there's no funny business going on. That's basically the way you can do it for regular files. Unfortunately, magic links throw a spanner in the works because you can actually mount on top of symlinks. And mounting on top of symlinks means that you can mount on top of magic links, which actually causes multiple issues. So you might think, oh, we can just do what we did before, just do resolve no xdev. Unfortunately, this resolve no xdev actually blocks the open because the file descriptor is on a different file system, so it's going to have to drop a different mount. And so this approach does not work. So you say, okay, well, how about if we do this? Okay, we'll just open proc, and then we do the verification I didn't put in, and then we open the parent directory, and then we reopen it. Sounds good, right? Unfortunately not, because you want to validate there are no overmounts because the final bit is not protected against them. And unfortunately, there's a race condition here because if if something mounts on top of you after you do the check, you're screwed. So what do we do now? Well, it turns out that the solution was lying in plain sight, which is we have the new mount API, which, by the way, for those of you who don't know, there are man pages now. I wrote them and they got merged, so we finally have man pages 7 years later. And you can buy 0, get 7 free. And yeah, effectively with the new mount API, the really nice thing about it is that you can get a handle that that no one else can mess with. So if you fs open it, no other process can do a mount on top of it, so there's no race condition concerns. And so in the simplest possible case, you can just do it like this. Now, here I say that unfortunately that's not always the case because if you are in an unprivileged, if you're in a user namespace, if you're creating a user namespace inside a container, so it's nested containers, if procfs has an overmount, this fsopen will fail because it violates the visibility rules of procfs, of the VFS, sorry. So what that means is that actually this approach doesn't work. So instead you need to use OpenTree and you will need to copy all the overmounts, which means that this validation is still required, but it is still race-free because even an OpenTree copy is still frozen and you can't get mount propagation events to it or anything. So it is still safe, but it requires a lot more work. And in particular, I haven't gone into it here because it's just mind-numbingly annoying. But effectively, if you're dealing with kernels pre-statex, checking that there's no overmounts is very painful, especially for symlinks. But yeah, that's that's for another time. If you're interested, you can read the source code and you can face palm as you read how painful it is. But the net result is that you just get this API where you can open exactly what you want, and it gives protection on brand new kernels. Use OpenR2. On older kernels, use OPAuth with extra verification, and it uses FSOpen if it can. If it's unprivileged, then it has to use the regular proc-open, but at least it's protected against non-racing attackers, which is the best you can do, unfortunately, for unprivileged users. Now, I'm sure there's some of you wondering, hang on, can't only root mount? Like, why does any of this matter if the only person who can mount is root? Like, why on earth should any of us care about this? And what on earth are you prattling on about? Well, unfortunately, we're dealing with the context of runc. And in the context of runc, we have a slight problem, which is that runc actually doesn't have a real threat model, which is very fun. And in particular, if you actually look at the history of runc bugs, almost all the vulnerabilities have been misconfiguration bugs. So this means effectively in the config.json, you set up some config that is unsafe. And the problem is that because it's a configuration, you can obviously configure things unsafely anyway, but some configurations seem more realistic for a higher level runtime to create, as opposed to others that are simply not allowed by higher level policies. And in particular, higher level runtimes, they let you set up mounts, but the mounts they let you set up are restricted based on their own policy rules and so on and so on. So yeah, it's difficult to get into like what is and isn't a vulnerability. And also, and this comes a great personal pain to say, most people still don't use user namespaces, right? Like it's been God knows how many years, and still people run everything as root and hope that it'll work out. Sorry. So we'll have a bit of a pop quiz. Is this a vulnerability? So what I've done is I've disabled all the namespaces in the container. Who thinks this is a vulnerability? No hands have gone up, and you're correct. It's not a vulnerability because obviously I've just disabled all security, so how could it be a vulnerability, right? So is this a vulnerability where I bind mount the root file system into the container? So oops. Probably no, nobody thinks it's a vulnerability. Yes? You think it is? So the thing is that it's not obvious how we would reject this without rejecting any kind of mount. So the thing is that from if you think from the perspective of Kubernetes, where Kubernetes, you give unprivileged user access to Kubernetes, you can create a security policy that does not allow mounting like this, and you can create a policy that only allows mounting volumes that are like generated by Kubernetes, which avoids this problem. Though actually one of the security vulnerabilities I mentioned where it was a Kubernetes one specifically in that code, but in theory it's fine. So yeah, I think the question is that from runc's perspective, while this is a very bad thing to do, in principle, the user could do it, and it's not clear like where the vulnerability sits here, because you would hope that. So again, runc is like a binary that you run yourself, and usually you're on sudo. So from runc's perspective, this is not a vulnerability, and also from like higher level runtime's perspective, they avoid this by not allowing you to do it, right? So at least from my perspective, I would say this is not a vulnerability. But now we have this. So is this a vulnerability? So I'm mounting some volume into some other directory in the thing. So in the container, I'm putting in /volume, and here I'm putting it in some volume path. Anyone think it's a vulnerability? It is a vulnerability. Now, I haven't told you several aspects of this, but it is actually a vulnerability because this actually was two of the vulnerabilities that we had last month were related, that had basically this exact same flow, but there are things that I haven't told you. In particular, I haven't told you that volume is actually a symlink to dev in the image. And also there is a racing process. There are several ways you can do this. One way is actually, it turns out Docker build lets you can use Docker build parallel builds to have one process swapping files while you're also creating a container in another process. And so, yeah, if you swap certain files inside volume with a symlink to proxys kernel core pattern, what you end up happening is that runc ends up trying to, so runc, there are certain bind mounts we have to do internally to have the system look like what a container would expect. In particular, for security, we have to mask certain files, and the way we do that is that we bind mount devnull on top of them. Now, we don't use devnull from the host because we were worried about container escapes, haha. So we use devnull from the container to mask them. So we bind mount devnull on top of files that we consider to be unsafe, including a lot of files in procfs. And then for creating dev console, we bind mount dev PTS and then the PTS number. So effectively by swapping it, you can make it so that rather than bind mounting devnull, I'm actually bind mounting proxys kernel core pattern on top of any masked file. And this is obviously, if you can write to this, you can escape a container because core Core dump helpers are not namespaced, so you can just configure a core dump helper and you can escape to the host, which is very good fun. Sorry. My bad. So the solution we have is that we added much stricter validation of special inodes, and in particular, the one takeaway I had from this was that from a kernel API perspective, having safe major minor numbers is super handy, because what it allows you to do is it allows you to open a file descriptor to a safe inode you want, so dev null, for instance, and you can actually just say, okay, I'm going to stat it, and I can check, is this actually the inode I was expecting? And this is very handy. We actually went and we audited all the special inode usage we have to harden it this way. But yeah, it's really nice the kernel does this, because you can imagine a world, okay, for dev null and stuff, it obviously needs to have a special number, but for PTYs, for instance, PTYs, they could have been random numbers, but actually PTYs have fixed numbers in their format, which lets you actually say, okay, I can check that the PTY number actually is 7, and then I can double check that the major minor number matches with what I'm expecting. So that's super handy. And then obviously we moved all the malware creation code over to the Pathras. So now everything is mostly Vardascript based. And yeah, regular path safety for this is a good idea, is I think a fairly obvious thing. But one example of moving everything to be Vardascript based is that this get PT peer ioctl is something I added to the console code a very long time ago. The PTY code, because to allow you to basically, once you have a master end, you can get the other end without ever having to touch the file system, so you can get it immediately, which is super handy, because then we don't have to ever touch dev PTS inside the container. We can just get it and we can mount it and we can be sure it's safe. So back to the pop quiz. Is this a vulnerability? So I mount like some random file on top of proc. The answer is no, because, well, if you could do this, there's nothing we can do to stop you. I mean, this is end up. I mean, maybe we should, in theory, block this, but at least we don't block it right now. But no high-level container runtime lets you do this, because obviously it's unsafe. So is this a vulnerability? So I bind mount on top of proc adder exec, app exec, proc1shed, and proc1shed is funny. It's a procfs file which you can write to and nothing happens. So it's a null write file. So it's very useful for these kinds of attacks, because it can make anything null. So this is also not a vulnerability. And in fact, runC will reject this, because we have a allow list of destinations in proc that you can mount on top of in an attempt to avoid these kinds of attacks. And that's not one of them. So you can't do it for that, at least. So what about this one? I think I'm showing my hand, because obviously the more complicated ones, the answer is going to be yes. But so the key thing to note here is that foo, and this is, so you have a bind mount of something to foo, and then you also bind mount through foo, through this, which the name is helpfully telling you it's a symlink, to thread self-adder app1. So congratulations to everyone who guessed the right answer, which is that yes, this is a vulnerability. And in particular, this is the third vulnerability we had that came out last month. And the way it works is that you have foo/symlink, foo/link is a symlink is being swapped between proc and some dummy directory. This is done to bypass some anti-proc mount checks we had. So again, we had this bug where we were trying to standardize paths, we were trying to check paths, and obviously those are race condition there. And then you actually get your own choice of which way you want to mess with the system. You can either make it a no-op by making proc1shed the target of app exec, or if you want to have lots of fun, you can make it proc sysoq trigger. And again, the very funny thing is, of course, there are lots of fun characters in exec and Docker default. And actually, I'm pretty sure T will crash your system. So, you get lots of spam and then your system dies. So lots of fun. And obviously, you can use the core pattern to do a container escape. You can't do it immediately, but if you set up a sysctl, runC allows certain sysctls if they're namespace, so you can set up networking sysctls if you have the network namespace enabled. But if you mount this on top of the network namespace, like procnet IP forward or something, net IP forward, you can just write any string you like and you can break out of the container. So the solutions we had here is that we beefed up our hardening when doing mounts. In particular, we reworked, as part of the rework for doing how we do mount procreation, we also changed everything so that all the mount points and all the mount sources are now done through file descriptors. We still use the old mount API, so my takeaway is we should have actually switched to that much earlier, many years earlier. But hey, they weren't doing man pages, but we have them now, so now there's no excuse. And yeah, we also switched to libpathrs for doing procfs writes to avoid all these problems for the procfs writes. Though actually, and this is sort of obvious in hindsight, we also audited every single write path in run C as well, because it's not just enough to block the procfs ones. If you write anywhere, anything can be misdirected. But it turns out that actually only the procfs ones were vulnerable, which is a bit ironic. So everything else is actually fine, but that's. Yeah, the one takeaway I had from this is because when we were dealing with this year, I also was developing the libpathrs procfs stuff in parallel, and I quickly discovered that actually it's very, very difficult to be absolutely sure that you are writing to the right procfs file. And if you like, I can talk a bit more about what kind of issues run into, but it's actually surprisingly difficult. So yeah, so from run C at least, the to-do we have right now, my biggest one is that I want to move out my infrastructure to the new Mount API entirely, because at the moment, we still use the old mount syscall, which we go through procself FD to try to make it a bit safer. And it is actually in practice safe because we have done different attacks on it. That part has not actually been attacked, but it would be nice to switch to the new mount API. In particular, one nice thing is that the application of masked paths would become atomic. So right now, because we do the mount and then you do, on top of it, you stack mounts afterwards. Theoretically, now run C doesn't allow you to run a container at the same time, so this actually shouldn't be possible to attack, at least with the container. But you can imagine a case where I do the proc mount and then some process managed to get access to underneath it and then the mounts happen afterwards. You can imagine a case where that would be a security issue. So, but if you switch to the new mount infrastructure, we can set up the entire mount tree and then put it on the file system in one go, which would avoid this particular problem. And obviously, I wanted to do a deep audit of all the path-based code in run C because the code was written like more than 10 years ago. And a lot, again, because Go pushes you to use path-based stuff, you end up with this sort of nonsense. And the other thing is that, as I mentioned, we had to use pathres lite, but actually you can use it you can use the real libpathres, which has more security hardenings, and you can actually use it as a backend using a build tag. There are some kernel to-dos I want to have, which is that there are some extensions that we've talked about a lot for OpenAT 2 over the years. One of them is that it'd be nice to have resolve for dot. So dot would not be allowed at all. This seems like it not be super useful, but actually, at least for me, it'd be useful for consistency because the procfs stuff that we have, if you don't have OpenAT 2, the procfs API it has like a very restrictive resolver that only works for procfs, and that one it can't support dot because it's not possible to guarantee the safety of it. So being able to use resolver dot for OpenAT 2 would mean that it would be consistent, but also people have asked about having this before. And if you have any other suggestions of kernel stuff you would like, I'm happy to hear it. The other one is that at the moment, OpenAT 2, the root file descriptor and the current directory are actually the same thing. And at the time when I wrote it, I thought this would be fine, no one would care. But obviously, I ran into a case where it would be nice to have. So maybe that's something that we'll add in the future. And yeah, unfortunately, a lot of the complications come from the fact that you can overmount magic links. If we couldn't do that, that would help a lot. And actually, some of them have been blocked. Probably even most of them have been blocked since 6.12. So at least part of the problem is solved, but obviously we still need the fallback code for all the kernels. Yeah. What else? I mean, for me at least, the general takeaway I had when working on this was that having a more file descriptor-based design and using stuff like libpathrs or just OpenAT 2 directly, it really it's not just a matter of it helps with obviously securing stuff, but actually it makes it much easier to reason about what kinds of operations you're doing because you have to keep in track. Rather than everything being parsed, scrambled everywhere, you have to actually think a little bit more about how you're going to structure things. So at least for me, I found it quite an interesting experience, even though it was very tiring, but it was at least interesting. And yeah, if you have any programs that you touch proc, you really should use something like libpathrs because it's actually it's like shockingly difficult to get right. And yeah, for me at least, now whenever I look at programs, like any program that has any path name syscall, it's there's almost certainly a bug there somewhere because there are so many ways it can go wrong. But yeah, so we actually had some fun issues which we found, which I wonder what your take on it is. So immediately after we released the security bug, we ended up with this bug report. I opened this, but we got bug reports put privately about it. So effectively, you can't write to. So will this only happen with nested containers? So with nested containers under LXC, AppArm will return e-access whenever we try to write to proxys anything. In this case, it was proxys net something, but for any proxys write, it would fail with an error from AppArmor. And if you turn off AppArmor, it just starts working again. And it was triggered by the switch to FS Open. Then we'll go back to the audience discussion. Does anyone have an idea what might cause this? Okay. I'll give you another piece of the puzzle. So when running in nested containers, LXC sets up an AppArmor profile that allows most writes to procfs, but it denies some things. But unfortunately, because AppArmor, this profile is written in a funny way, just because AppArmor requires you to write it that way. But the key thing is that it allowed writes to proc sysnet. So if you were to just try to write it in the container, it would just work, right? Any ideas? Okay, if I give you a hint that actually this is relevant, so okay, proc sys has these rules, but sys has different rules. Okay, and if you delete the sys rules, writes to proc sys start working. Okay. It's not the right. It's not the right regex. But good guess. No, it's because of dpath. Because when runc does fs open of proc, because it is a mount in a isolated mount in an anonymous mount namespace and is the root of the mount, to dpath it looks like slash. So when I try to write to sys foobar to AppArmor, it looks like I'm writing to slash sys foobar, and so then it just sees the wrong path. And yeah, I was hoping if there'll be some AppArmor people, we could have a discussion about how we can solve this, because this seems very interesting behavior. Because yeah, and actually the funniest part is, and so yeah, AppArmor gives you access. And the funniest part is actually you can actually get this. You can do this with tempfs, so you don't have to do it with procfs or anything. You can just create tempfs and then try to create a directory called sys and then sysfoo, and AppArmor will block it even though it's just a regular directory. Yeah, which was very good fun. And then yeah, the solution we had, unfortunately in runc we couldn't do anything. I tried to come up with some solutions, but unfortunately none of them worked. So one of them was that I could make like a tempfs with a proc and then mount the proc inside that. But that doesn't work because dpath can't walk outside the mount because it's a detached mount. The rules for dpath are a bit different. Christian nacked me when I suggested that we change that. So that wasn't an option. And there were some other attempts to try, but basically nothing worked. So yeah, the solution was that the other runtime, so LXC and Incus and so on, would have to just disable those parts of their profiles, which is not ideal. So again, would love to be able to speak to some AppArmor people if we can fix that. And then yeah, another fun one is so previously we expanded all symlinks lexically, which is wrong. So we would, oh no, that's not true. When we expanded symlinks, if we hit a non-existent path, we would just keep walking as if the paths existed. This was basically a bug in some very old code that existed in Docker a long time ago, and we had to keep it around for compatibility. But the net result is you end up with cases like foobar, if it points to some non-existent path, then if you want to try to create like a mount point in foobar baz, it would create the mount point at some non-existent path baz, which isn't how dangling symlinks work on Linux normally, and normally you would get enoent or you would get some other behavior, but you don't get this behavior. Unfortunately, when we switched to file script-based stuff, this stopped working, because if you write the program properly, it shouldn't do that. Unfortunately, some users depended on this, and it turns out there are a bunch of images that have like symlinks to random paths that don't exist, and it just happens to have worked so far. So yes, we had to fix this in a kind of awful way, which is that we expand the path the old-fashioned way, and then we use the file descriptor approach to actually operate on it safely, which is less than ideal, but it was the only way we could, we could keep things working. But yeah, so I have a bit of stuff about libuffers afterwards, but I just want to ask if anyone has any questions. Yes. Sorry.
Thank you very much for the talk. So there is an interesting another class of users, of developers that deals with path safety. People who run sandboxes for software and especially build systems.
Yeah.
For example, I'm a Nix developer, and we run all builds that user provides in a user namespace.
Yeah.
And what we want to avoid is something similar to container engines, two builds that cooperates with each other and try to attack and get advantage and so on. And we run into all the same bugs and so on. Interestingly, our biggest problem regarding path safety is multi-platform support. So Linux has a lot of nice APIs, OpenAD2 and so on, and we sometimes have issues. Other operating system doesn't share this joy.
Yes.
So this makes writing code cross-platform very, very complicated, and increase the chance of doing it wrong. Another interesting thing is, so the libraries you presented, they all work on many, I would say, environment and platforms. One that is missing is C++, I feel.
Right. Yeah, you'd have to use it as if it was a C library. Yeah.
Right.
It's unfortunate.
Correct. But in C++, something we really want to do is have a RI, like a proper wrapper that auto closes things and so on.
Yeah.
And Chromium made an interesting thing called save file descriptor that uses OpenAT2 and all that stuff and forces you to have like a proper development style for, well, doing all these things right.
Okay, that's interesting.
Yeah.
No, I'll definitely take a look. For the first point, what I want to say is that, yeah, so for other operating systems, I mean, they don't, well, some of them don't have OpenAT2. FreeBSD, now they have, okay, the history is kind of funny where FreeBSD had O beneath, and then but it had a fairly fatal, well, not fatal, it had a flaw in it in how it did something, and you actually could escape it. When I did OpenAT2, I based resolve beneath based on FreeBSD, but without the bug, and then now they have O resolve beneath, which is basically OpenAT2's resolve beneath. So at least for resolve beneath, you can get on FreeBSD. But yeah, for the OPATH stuff, the main problem is that when you walk into ... you need to be able to, this is actually, the kernel does the same thing. So you can't, when you go into ... you need to validate that you are still with it where you expect. In the case of the kernel will just return, if there's been any rename or mount on the system, it returns E again. The idea being that the user space can then do a retry if they want. But for user space, in order to avoid that, we need to go through procfs to check whether .dot is safe. However, the approach that Go did with os.root is actually quite interesting. Though it probably, I think it has scalability problems, but like it actually is cross-platform. So the idea they had was that effectively you like keep track of what path you're supposed to be in. And if you hit ... then you rewalk from the root with your like logical path again. And that should work on any platform, at least with Go. I think they support that. I think they even support it on WASM. Like they have it for most platforms.
I have two very quick last questions. First is, do you know of a formal model about how paths works? Like, is there any academia research that tries to put an end to this mess of how do we do path?
Not that I'm aware of. And actually, the annoying thing is that Linux has, as I found out when I was working on the OPATH stuff, and I was writing tests with various different setups and so on. What I quickly found is that the straightforward approach of using OPATH is actually quite wrong. In particular, most people forget to handle how unprivileged symlinks work. Most people forget how to handle whether or not it has a like if you have a no sim follow as a mount flag. Most people forget to check for that. So if you walked into a no sim follow symlink, you could accidentally follow it, and so on and so on. So I think I don't know. It's possible someone has looked at it. I'd be interested to know if someone has looked into it. But the thing is that at least with Linux, the VFS stuff, I mean, a lot of it changes release to release. And so while I think the broad, if you were to look at like whatever V7 Unix and like what is the general model of Unix paths look like, that might be interesting. But from a day-to-day perspective, I think that there's all these other things that get added, which cause different kinds of problems.
And my last question is, do you know anything about path safety or strict path safety for C groups?
So in run C, we just use resolve no xdev. So because they're all regular files, so you can just use it. And actually, that was the first usage of OpenAT2 in run C was for C groups. So C group v1 is slightly more annoying to deal with, but C group v2 is you can check. Okay, from memory, I think that the root. I would need to double check that. I think that the root inode of sysfsc group is fixed. I would need to double check that. But if it is fixed, then you can just open sysfsc group, check that it has it's the right magic number, and also it has the right inode number, and then you can just use resolve nextdev. So at least that's. And actually, the thing I want to mention was the reason why procfs is so important is because obviously, sysfs also contains a lot of other files you don't want people to write to. Luckily, at least in run C, we don't support like run C doing the writing to sysfs, so at least we don't have to worry about that. But actually, the thing is that once you have procfs, because procselfd gives you the dpath of any file you open, if you have a safe procfs resolver, then you can open the file descriptor to the sysfs file you want to write to, and then you can check whether or not it has the right path in procselfd. Now, that could error out in certain cases, but the benefit is that it will never give you at least it shouldn't ever give you the answer of this is the path you wanted, but actually is a different path. And so that's why I harp on procfs, because at least with procfs, in principle, all the other strict path safety stuff can just be done by checking it. Now again, that only works on Linux; it doesn't work on anything else. But yeah.
Thank you so much.
No worries.
I wonder how all of those CVs were discovered.
Some of them were by me actually, but I think that so. The interesting thing is that when we actually I can probably go back to if I remember what slide it was. This is the problem with having too many slides. That was before that. Okay. So the funny thing is that so when we and actually I excluded there were some bugs from before them that didn't have CVs assigned or were like a little bit more complicated. But when I think I reported this one, the 2018 one, and one of the things I did was I provided like some very generic exploit scripts that you can use with stuff. And I think what happened is that some people used them to find other bugs, and then other people just looked at the previous research and just said, oh, I wonder if this other random bit of path stuff has this particular bug. So it wasn't found through fuzzing or anything. I mean, as far as I know, it was all just people looking at it. But the thing is that it's one of those things where effectively you can look at any API for most programs, and if it has something that has to do with paths where you have access to it, either it's very likely to have a bug like this, or they're lucky. That's my view at least. Because the thing is, people have tried. I mean. Like actually the funny part is I didn't include the details of this one, but this 2018 bug was in Docker CP, and what they did was that they actually used chroot to try to protect against these attacks. Unfortunately, they chrooted into an attacker controlled path. So you could just if you change the symlink of the parent, then you could chroot into / on the host, and then it doesn't matter that they have a chroot. So yeah, that's.
I just see that those are discovered every year. So if it wasn't fast, for example, I would assume that. Well, why they will do this if not?
Yeah. So
but on the other side.
Yeah. So I mean, I think probably you could try starting automating it. But what I would say is that from my perspective at least, because a lot of these that were at least related to run C or related to something with run C, it seems to me that each year's version, when we get our yearly security issues, they tend to be an evolution of the previous ones. So the original ones from way before were not even race-based. It was just purely we forgot to standardize paths properly, and then we started having race-based attacks, and then we had procfs attacks that were very trivial, and then the ones we had last year were actually when I first analyzed the ones from the procfs ones we had ages ago, I had a feeling we would have these kinds of attacks, but it required a lot of the other infrastructure that wasn't ready yet. So I was hoping we could fix it before attackers found it, but unfortunately they found it before we could fix it. So yeah. Yeah, I'm sure. Actually, it seems like one of the things you could automate. I don't know why no one has, because it's yeah.
You mentioned that FD-based approach is a better one.
Yes.
I wonder, like, isn't it the case that just using files and file operations to express system calls was a big mistake? And isn't it better just present all of the procfs and say cgroupfs things as actual system calls that would avoid all of those problems altogether?
Yeah, I mean that's the classic argument, right? For yeah, yeah. So the thing is that I think there are several aspects, especially when I talked about the attacks we just had recently. There are several bits of them that are like could never happen if it was syscall based, right? And so that really makes you wonder whether or not it even makes it. For instance, the sysctl one. If it was syscall based, then there is no way you could accidentally write to the wrong sysctl, right? And the fact that that's even possible is very, very strange. On the other hand, and this is as is always the case in Linux, the fact you can do it also provides other nice benefits. So for instance, one of the things that is used by some container runtimes like LXC does this, they have fake procfs files that they use Fuse for. So they have a Fuse FS called LXCFS, which then bind mounts on top of proc meminfo and proc CPU info to provide fake information about what CPUs and what memory is available. Because proc is not containerized, at least it doesn't contain cgroup, it doesn't contain what your cgroup's actually limit is. So for older programs that weren't cgroup aware, this was a very useful way of being able to migrate programs. And there was cases where if you ran Java without this, it would like crash. It would stall the system because it would try to allocate like 20 times more memory than it has access to. So it's difficult. Is it? I mean, to me, yeah. I don't know. I go back and forth on it because it seems like yeah, we could avoid the problems, but yeah.
There are also ways to intercept and emulate system calls.
Yeah, with Secom Notify you can, right?
Do this, so it's not. Like you don't need to have files.
Sure. I mean that's much newer than the mount approach, right? But yeah.
Okay, I think we can get one more question in. I think I saw a hand at the back there. Or no? Okay. Well then, we're pretty much at time. So thank you very much.
Right. Thank you so much.
And we will resume in half an hour after the break.
The most interesting man in the world. I knew it wasn't.
Or do you want to do the handheld? I'm going to sit in the middle so you might see me this time. Yep.
Is that on? It's 81 slides. What? Is that mine? How do I get that? I don't think that's my slides.
No, it isn't.
Okay.
Kate, for not switching it over before she left the
It's
room.
okay.
There we go. Let it go. Huh? That's what happens when you start with the.
That's all right. Just doing that right there. Just hit the thing. Yes.
Yes.
There it is. Cool. Thank you.
Okay, I think we're ready to restart. Hope you all had a good break. And up next is Chuck Wobler, and he'll be talking a little bit about some of the findings we've been having.
Yes. Can you guys hear me? Okay. My name is Chuck Wolber. I've been working with Gabrielle Pallini and Kate Stewart on crossing the semantic gap. Really what we're talking about is finding a way to collect all the design information that gets lost when you go from your brain to code that's useful, and testing should be done between that. But first, let's start with, let's see, I just click it like that. Okay. Yep, let's start with some information, some numbers. So this is just commits from the mainline repository. There's about 1.4 million non-merge commits, and then 1.3 million non-merge commits. I learned something interesting about Git when I was putting this together. There are, in the mainline repository, 101 commits where the parent commit, the commit time happened happened after the child commit. So either someone reordered it or anything like that. So I learned something new. If you do, if you're bracketing in on your query using Git since and before, if you do that, you're going to miss 101 queries. So I'll leave that as a puzzle to you. There is a workaround that they added an argument to Git to work around this problem.
By the way, I think the when you get AM, it takes the timestamp of like the patch.
The commit time. So since and after use the not the author time, the commit time. And there's 101 patches that are excluded when you do it that way. So there's another argument you have to do when you find it. So that was another non-obvious design aspect. Somebody had encountered before I did. So let's start with that. But that's not very useful. Let's go to some graphs here. These are mainline commits per hour. We are approaching about 10 commits per hour. This is steady state. The gap between the red and the blue, of course, is probably a proxy for maintainer behavior. Those are merged commits. About 45% of that gap is just Linus alone. The rest is other maintainers. So I guess if you're MBA in business school, you could say the distance between those is a proxy for how productive the red line is down to the bottom. So if you're really looking for good metrics, there's something. Also, it probably is a sign that Linus Torvalds is one of the greatest managers in all of business history. So go with that too. This is a steady state increase in maintainers. Generally, I did this based on unique email addresses in the maintainer file. There's no way to tell if the same name associated with multiple email addresses is the same person. I don't know if name duplication. Mail maps, no help there. So, but I think this is fairly accurate. We're about 2,000 maintainers right now in the Linux kernel. And if you were to divide that over the non-merged commits, just the workhorse commits, I guess, you get this interesting graph where it peaked and then slowly steadies down. Obviously, the real information is much more of a long tail. So there's some very prolific maintainers who do a lot of merging and other maintainers who don't have to do a lot. But over the long average, it's interesting to see that as maintainers have increased. So now we're, across everybody, we're actually, like 40 commits per year per maintainer on that basis. Now, if we look at the fixed commit rate, this is where it gets really interesting. There's a fixed tag. There's a ramp up, so I would kind of ignore all the data before up to 2019. We're getting our act together. There's better tools, that kind of thing. But going forward, we're approaching probably about 20% of the commits fix one or more issues. So that's quite a bit. A lot of fixes. That's the sign of a healthy project, of course, right? It'd be unhealthy if it was really low. It means we're either not documenting the commits, but also this is just a baseline. All the fixed behavior is this is the minimum level. There's a lot of things get fixed or changed in re-architecting and new systems or alterations that aren't noted. So at a minimum, so we're probably much higher than this actually as far as fixes go. But like I said, there's a lot of fixed behavior going on. Okay, and it's interesting. So the last graph I'm going to show you is this is sort of commits per hour overlaid with your fixed commits. So it's about it's about 2 commits per hour of the close to 9 or so non-merge commits that are fixes. So that's what it's like a little over 20% of the stuff going in, like as we're talking here. Okay, all right. So that's the big view. Let's narrow down into a case study view. And first thing I want to do is thank you, Steve Rosted, for being very helpful to us. You have gone way above and beyond, and I hope the work we've been doing with ftrace and reverse engineering it has been helpful to you. But I just wanted to publicly thank you for being there for us and helping us out. It has really meant a lot. Steve showed up at the 2024 Linux Plumbers Conference. 2024 was not the first time we discussed this. It's kind of where we started to get ahead of steam. Steve gave us the homework, along with Thomas Gleixner, develop a machine-readable template for this crazy idea we've got going on, right? We need to be able to tell. We'll go into more about that. In the 2024 Alyssa Goddard workshop, Steve showed up in person and took a look at our template, had a lot of good feedback, and he said, reverse engineer my subsystem, ftrace, and I'll give you some feedback on it. So, okay. Gabriele Paolini went back and reverse engineered a small portion of it. Okay, got a lot of really good information. Steve again showed up in person at a Zoom meeting. Okay, so we could show him like an A/B to see what he thought. Okay, and then of course Steve has done, along with the rest other maintainers, multiple patch reviews, detailed feedback, and even a code merge. We got to change in the mainline. Okay, so let's look at what we did. Gab analyzed a small portion of trace events.c. What did it result in? One fix got accepted into mainline. We weren't trying to fix bugs. We're just reverse engineering the design. We looked at a small section, a very small section. We said, huh, that's interesting. And it turns out it was a legitimate fix. We got another one that's, we got to document the behavior. To actually change that would require a major redesign. It's just not going to work out. So we're just going to document the behavior. We were not headed after these things. We just dug deep into the code and we found these things. It's what happens. But beyond that, Gab did a bunch of kernel doc submissions, okay, on these areas. You can find those, there's links to them, okay? But the important aspect here, hold on. Is that going? Okay. Before I go on, let's look at the mainline fix. This was silent failures, okay, that we uncovered as part of this. We weren't headed after that. We're just trying to reverse engineer the design. Let's look at the other one. This ended up being a documented one. I purposely only put part of the patch that Gab wrote and Gab originally submitted, okay? I just wanted to show, everybody who's written code knows that if you're reading too much off of a buffer, that's not a good sign, right? So I purposely just picked the scary part of the patch. We didn't know what we're looking at when we looked at the ftrace code, so we didn't know, is this good, bad, I don't know. It was analyzed on the mailing list, and it turns out, no, it's not something we're gonna be able to fix, okay? It's never been reported as an issue. This required a lot of knowledge that we didn't have when we looked at the code, okay? So it took the experts to come up with this knowledge, to help us with this. So we conclude, we only analyzed about 10% of one file, okay? That resulted in 8 discrete threads on Linux trace kernel, 21 emails authored by Gab, 9 by Steve, and Masami 4, okay? Contributed to this. That's a lot of work. I mean, if you add up all the time, anybody who's a maintainer, anybody who spends time looking at this stuff, you put your time into it, your heart and soul into it, you love your work, okay? This is time expended to dig out design information that's hidden, its assumptions, walking around inside the code, okay? The mainline fix and behavior documentation, this is evidence of untested and undocumented functionality. That's fine. But you saw that all the metrics I showed about the Linux kernel. We just looked at one tiny corner of the kernel, and we saw a lot of this. Not a lot of this, but we found legitimate bugs, things that needed to be puzzled over, things the experts needed to think about.
It could just be that I'm a poor programmer.
Nope, that is absolutely not the case. Okay, all right. So I got 2 more examples. Preempt RT scheduling, anybody involved in that, 25 years, okay? They had to go back and reverse engineer the behavior of the schedule, to develop a preempt RT patch. It wasn't known, okay? It's a lot of work. And all that work went into developing a lot of code patches to make the Linux kernel a real-time OS right off of mainline, okay? But that information was, we've all done this, right? You spent a lot of time, oh, that's interesting, I don't know about that. And where do you put that? Okay, this is what I'm getting at, is we're trying to come up with a way of where you put that. And one more, okay, one more. This is the Rust discussion that came to a wonderful resolution here at the Maintainer Summit, okay? Case's comment right here. Doing so would actually carry a lot of risk. We don't want to replace the existing code because doing so would carry a lot of risk. Why? Why code stabilizes? Because we haven't written down all the unstated assumptions. As you write code, the ideas in your head do not get conveyed to a declarative nature like source code, okay? It becomes, it's great code, but it becomes fragile because it would carry a lot of risk to change it. This is a case in point. There are thousands of these. It wasn't hard to find quotable elements like this, okay? So the general conclusion, reverse engineering the intended behavior of the kernel is really hard. It's interesting, it's great, but it's very difficult. Questions of intended behavior require precious maintainer time. Maintainer attention is the rarest resource on the planet here, right? And when you don't know what you're looking at, you think you're looking at something you don't know, you got to ask. And then the maintainer, if they're gracious enough like Steve is, has to spend some of his valuable time to answer. And it's great when we get that and it leaves breadcrumbs on the mailing list, but how does that translate into testability? So nothing exists. Basically, the high-level thing is nothing exists to uniformly capture valuable expenditure of maintainer time and attention. It's in the mailing list, okay? It's there, okay? But is this reusable? Does it inform tests? Ensure, nothing exists to ensure subsequent code changes reliably reflect original design intent. When I change the code, is it still abiding by the original intention? If we even have the original intention, okay? Nothing exists to reliably tie automated testing to intended behavior. There's a lot of great testing, but nothing, that work we did on the mailing list, is it being translated in real time to the automated testing? When someone makes a code change, is it being translated in real time to any automated testing change if the intention change is part of the code change? Nothing exists to do that, okay? Nothing exists to alert, hey, it's time to take a look at that. And nothing exists to trace maintainer sign off. Did we get it right, okay? Is there a process around this? Is this a familiar thing? Not everybody's got the general, It's a great community. I don't want to say anything bad about the community, but I'm saying like Steve gave us a lot of his time and was willing to look into this, okay? But is there a process there so a maintainer can easily go, yes, no, I don't even know what you're asking here. I've never seen this question you're asking here. So, went too far. So as we're working through this, Greg gave us some homework too to look at one of his subsystems. And it boiled down to this conversation here. So what? Okay, Greg said, for some reason, Linux has succeeded without this stuff. Why do we need it now? We've been here for 3 decades. We'll be here for 3 decades more. And I said, absolutely, I agree, okay? But with the exception of some very narrow situations, the emergent design or nuanced complexity of the Linux kernel isn't communicated in a broadly consistent way. Even veteran kernel maintainers are tripping over nuance and complexity. You can find it in mailing lists. It's all over. At this conference, a lot of these sessions are about digging into nuance and complexity, okay? And Greg's like, correctly, in fact, he says, we all trip over nuance and complexity. Coding is hard, right? But adding formal comments is not going to solve this. Proof is on us. Totally agree. Completely agree. Okay? So let's look at what we're doing right now. We have long-form project documentation. It's actually really good documentation. It's interesting to read. We have mailing lists, a lot of really good records, commit history. It's interesting to go from the very first few commits in the mainline repository to now. They get longer, more detailed, more robust. It's great. It's neat to be able to see the evolution. We have seasoned intuition. Maintainers are maintainers because they're really good at what they do, okay? And they've got a lot of knowledge in their head. The hallway track is incredibly valuable. Okay, of course we have syscaller, k-self-test, k-unit, vendor test suites, and the list goes on. Okay, but testing is fundamentally guesswork. Testing is driven by interpretations of behavior. They're educated interpretations, not maintainer confirmed design intent. Did we get this right? And then when a change comes in, can you link, did we still get it right? And precious maintainer time is wasted. Valuable insights that we discuss here, even if it's not being asked twice, okay? The valuable insight exists on a mailing list, doesn't exist in a way that can tie it to testing, that can tie it to new people that come along, that can even tie it to the maintainer themselves, who needs to refresh their own memory. So I define the semantic gap this way. Code is declarative, intent is inferred. Therefore, coding is a lossy process. Just like when you compile code, there's no such thing as a reverse compiler for the same reason. When you go from idea to code, it's a lossy process. Intent is lost when ideas are converted to declarations. Smart developers who've seen this pattern before can put the big picture together. But guys, we're working on a kernel. This is not something that's on billboards every day. This is a very, very, very complicated device. Thinking about developer skill, saying just write cleaner code. Okay, relying on developer skill to write code that is full and unambiguous, its intent is reliably inferred, is not a viable solution. Okay, complexity and size will eventually overcome your available resources. Now, there's no excuse to accept spaghetti code. Okay, you should take pride in your work. You should demand people you work with take pride in their work. What we need to recognize is there's a practical limit to what design intent can be inferred from even those beautifully developed code. Okay. So is there a small and maintainable way to uniformly record design intent as it's discovered? It's always going to be an organic process. The design of the Linux kernel is emergent. There should be a way to record stuff as it comes along. So let's go back to ftrace. On April 4th, 2005, Steve graciously agreed to take his time and join us in an in-person Zoom meeting. We were going to show off an A/B test of the proposed methods. So apologies, it's an eye chart. It's not meant to be read here. Okay. This is one version. I'm just going to go right to the feedback. Okay. And Steve's okay, I guess. That's the other reason I want to hear, Steve. You could correct the record if I got it wrong. But okay, I guess it looks like pseudocode though. I'm not sure how useful that is. He's being very polite, of course. We agree, and so do a lot of other people. What I have here is a quote here. Even the highly regulated industries say, yeah, it's not, you can't pseudocode your design. Okay, it shows little intellectual effort or understanding of actually what's going, the actual intent. So that's not what we're after here. So then we showed them this. Again, it's an eye chart, but it's more declarative, okay? Give you an example. If soft disable is 1 and the trace event reference count is 0 and so on and so forth, it tells you what should be happening when and what your expectations are, okay? Shows you what you expect of the code. We're still working on the format and the design. It's a little verbose right now, okay? But the intent should be clear. We're not repeating the code. We're telling what the intent of the code is supposed to do. Now, my recollection, Steve, you can correct me if I'm wrong, was, oh my God, this is great. I remember you got excited. This is exactly what I need. I even have some of my own code that's so complex I have to relearn it every time I have to work on it. This would save me so much time. But wait, let's go back to what Greg said. We all trip over nuance and complexity. I don't believe adding more formal comments is going to solve that. Proof is on us. Well, I completely agree. I totally agree. Because that's not what we're doing here, okay? This is not a slippery slope into formal verification. By the way, even I work in one of the most highly regulated industries in the world. We are not required to do formal verification for even the most highly regulated, highly audited pieces. We have to define our design and make sure our implementation matches our design. Code and test has to come from the same central idea. That's all it is. That's all it is. And that's what we're trying to convey here. We're not trying to repeat the code in a different language. This is not just repetition of pseudo. That was a pseudocode example. We're not trying to do that. That's a waste of everybody's time. We're not trying to apply rigid language policing based on arcane academic rules of thou shalt do this, okay? Might see the word shall in here and that thing, but words have meaning, okay? It's just about definitions and clarity and succinctness. We're not trying to create a new process mandate. This is an organic approach. This is a way to say, hey, when you get a nugget of useful design intent, this is how you should add it to the kernel. This is how we keep it. This is how we make it useful. This is how it can be conveyed to test and everybody else coming along. And this is no way involved, related to, or supported by AI. This is not an AI tool. We're not inputs. I'm not interested in creating this from AI, okay? This requires a very deep, complex understanding of the code. This requires adhering to the pattern. This requires adding as we learn more. This requires editing as we learn more, okay? This is not for AI tools. This is definitely not something specifically meant for a regulated industry. It might be useful, but it is not meant for that. This is about saving maintainer time, saving everybody's time. So what is it? Capture, follow, test, and trace. This is a voluntary method for uniformly collecting lost design intent, lost or never known, as you find it, when you find it. Give you a place to put it. Follow, okay? This helps you follow. So the design, the code itself can follow. I'm sorry, the design and code can stay in sync. Test can stay in sync. They all follow each other. Test is just a reliable method to bind code and test to intended design. Make sure you're working from the same page. And then, of course, trace. This is a simplified approach to maintainer sign-off of intended behavior. Now, I work in an industry that uses the word requirements a lot, and that never really landed with me, so I always just kind of say, it's what you expect from the code. It's what you want. It's your intent. It's your expectations. And they have to be testable, so I'm just calling it testable expectations. You can call it requirements if you want. It doesn't really hit with me. Testable expectations, okay? Okay, fine, but I see some problems here. These are not, this is stuff that has been sent to us. People have asked us these questions, and these are our answers to them, okay? Comments don't compile. How do you keep this in sync? What's your plan here? Who's gonna write these things? How long is this gonna take? And how do we know they're complete or even correct? Let me give you an answer for those. And if you have more when I'm done, I'd be happy to entertain those as well. So comments don't compile. This is one of the early homework assignments that we got from Steve and Tomas. We need some way of building a template. This is, of course, a draft, okay? This is a machine-readable template. It's meant for the human-readable, testable expectations. Built into this is a checksum method where we tie code and testable expectations together. So you have one is a unique stable ID that you can always trace to. And then two, you got what we call a hash key that will float as you change. So imagine you've got some CI or automation that just calculates, and every time a checksum doesn't match up, someone has to go in and say, code changed or testable expectation changed. Do I need to reword this? And then, of course, if you have an automated test environment, somebody else does, they can see when those checksum change because the git commit log is public. That causes all the propagation to occur. These are some of the tags we're discussing right now. It's all draft, okay? A lot of good work going on with respect to these right now. Let's see. Oh, no. Got it? Yes, okay. Who's going to write these things? Anybody who wishes to capture design intent, hallway conversation, anybody say, oh yeah, we figured that out. Well, let's add this, okay? Let's add this nugget of information. It gives you a way to do it. Gives you a safe place to put it that's well understood and is reusable. A lot of times that ephemeral information is like, well, I have it, you have it. But how do you keep it? How do we make it useful? So anybody tired of regressions, relearning their own code, fragile, unmaintained code, as you learn something, it gives you a place to store that information in a useful way. Testers trying to understand the code, newcomers, and even industry participants who just want better testing and traceability, they can write them. We just have to provide a framework for them to do it, okay? And then how long is it gonna take? When are you gonna be done with this? I wanna see all this design in there and then I want you to get off my back. That's not how it works. It's not that question, that's the wrong question. I reject the premise of that question, okay? It's not about how long it's gonna take. It'll take as long as it takes to finish the kernel. It's really a question of respecting everybody's time, giving them a place to put the useful information, the design intent as it's discovered, okay? When hard work goes into learning something about design intent, this is a method for uniformly capturing it. And then we can make it useful to a broad audience. Obviously, kernel maintainers, that's really who it's meant for. For committers, anybody who's writing kernel code, testers, newcomers, anybody who uncovers subtle bugs or tricky edge cases, a lot of that. And then, of course, any industry consumers too. How do we even know they're complete or correct, right? How do we know this is not garbage? So there's a few documented basics. We're working on some documentation for the kernel documentation that tell how to do this, right? You need to be concise. You can't make negative, untestable statements. That just won't work. And then you got to be precise with your words. But correctness and completeness is not an initial goal. This is an eventual consistency problem, okay? Correctness and completeness happen organically through what we're calling the virtuous cycle. You have a testable expectation. If somebody went to the trouble to write it, okay, it's always usually written after. It's probably always going to be. It will always be written after the code, long after the code's been written. Okay, automated test. If it uses that testable expectation, and then you got code coverage, making sure you're hitting all the code. If you have a bug, you discover a bug. Okay, it's either an invalid or missing testable expectation, or it's an invalid or missing test case. If you have a test failure, we call that a verification failure. Okay, it could be an invalid testable expectation, or it could just be a code bug. Over time, they all sync each other up. Okay, you get a better description of your design, you get a better way of testing it. The code is now in sync with all those things. You will constantly discover more testable expectation, more design intent. It just goes into the mix. You have a testable expectation with no test case written on it. Guess what? That's a job for the tester to write a test case for it. Okay? The code doesn't match. Fine. It all syncs up over time. So, and with requirement, test, coverage, and coverage in equilibrium, it becomes possible to assert the code is an accurate reflection of the developer intent. That's called the verification cycle in some circles. Okay? The validation cycle is, did it do what I wanted it to do? I don't know, but at least it did it the way it was specified. So there's a difference between validation and verification in that respect. So walk me through the process, okay? Code always comes first. That's just always the way it's gonna work with the Linux kernel. There will never be a time when someone writes testable expectations that go along with the code. I hope there's not. That go along with the code. I never wanna lose that spirit, okay? There's always the maintainer review, the sign off, the merge into mainline, and so off, they run off into the sunset. The kernel doc, this is gonna be kernel doc, testable expectations, they always lag the code. This is a feature. It just means we have signaling to let us know when it's not in sync. That's it. CI or automation notes that the checksum is mismatching on an existing testable expectation. Anybody's free to go in and fix it. There's probably gonna be a maintainer community that builds up around this. When there's useful and interesting work to do, we always tend to find people to do it. We have 2,000 maintainers now. I'm pretty optimistic we'll have plenty of people who are interested in doing this sort of thing, okay? It's a different task than coding. So the kernel doc testable expectation pass will just go through the same maintainer sign off. But in this case, now we're talking about, hey, did I get it right? Steve, did I get it right? He can go signed out, yeah, you did, or no, you didn't. But eventually we get that all important sign off that said, obviously not guaranteeing, we're not holding anybody's children hostage here, but we're saying to a reasonable degree of accuracy, I am the expert here and I think that's about right. Now we can go back and fix that if we need to, but we have that traceable sign off, okay? There may be a possible testable expectation maintainer, someone who's there to educate people. Hey, You can't prove a negative. You can't say shall not have bugs. That won't work. So maybe we can fix that. So there may need to be some of that. But it's a minor hygiene thing about how to write testable statements in succinct ways. Of course, then you have CI or automation that notes checksum, kernel doc, check some changes, right? And then test environments, they can go say, oh, well, we need to update, we need to check our test cases. Right? So there's traceability all the way through, alerts the right humans that someone needs to check and update. I think that, there it goes. So the call to action. We want you to push back and point out flaws, point out what we're missing. We need feedback. We want you to engage in constructive dialogue, okay? Look out for the kernel doc testable expectation patches on a mailing list near you and provide feedback, especially if you're a maintainer. And if you want us to take a look at your subsystem, please tell us. We don't have all the time in the world, okay? But if you have something interesting you want us to look at, particularly if it's like unmaintained and maybe you inherited it, we might be able to help you out. Contact us, let me know, okay? And then contact us if you want to participate. We're still working on the template. We want to do a lot of automation. All right. Obviously, it would be great if we had people who want to throw down and help reverse engineer the kernel. I think everybody would benefit from that. And of course, work with other groups. We want to close that virtuous cycle so we can organically bring all this together. Design, test, and code, bring it all together. So work with other groups and bring the message to them. So with that, thank you very much for listening. I appreciate it. Open the floor to questions. Yep. Thank you.
Hi.
Hi.
Well, the question that comes to my mind is, if you're asking people to write testable expectations, why don't you ask them to write test cases?
What we want, so the answer is great, yes, absolutely. All we're trying to do is make sure that test case and code come from a central idea that the human understands. That's all we're trying to do. Yeah. So like, please don't skip the step, like work from the same thing. That's all.
Let me explain where this comes from.
Sure.
I don't work much in upstream, but I do maintain an internal kernel tree. Mm-hmm. I do not merge anything that doesn't come with test cases of its own because I want to see how guys did verify their own stuff. Mm-hmm. So why not doing this and skipping the intermediate step, at least for new code?
And it's a good thing that all maintainers are writing test cases for all of their code. And it's awesome that like...
But here what I'm trying to ask is, to me it seems that you have two problems. One is retrofitting this to old stuff, and the other one is somehow handle...
Yeah, no one's suggesting we're going to boil the ocean here. There's a community of test case writers. There's a community of coders. We're trying to like look back in 10 years time and say, yeah, we started writing testable expectations and the test case writers started to use those. That's cool. And the coders, right, it started to show up in kernel doc. So this is going to happen organically. We're not going to like stop the car here.
Oh, yeah. I just want to correct something about tests, or something you just said was testing, like, oh, all maintainers test. At Maintainer Summit, Linus was saying, he specifically said when he gets pulls a commit, does a build, and it does his current thing breaks, and he looks at the code and goes, this obviously wasn't tested. If you really want to piss off Linus as a maintainer, send him code that's not tested.
Yes. Yeah.
Could you please show me an example of a testable assertion?
Oh, yeah, I'm sorry. Thank you. Yes.
Could you please show me an example of a testable assertion?
Well, it's a bit of an eye chart, but that was the B test.
Right.
And I'll go back to it. Yeah.
Please.
I can go back to it. There we go. So I apologize. It wasn't meant to be read. I try not to read from slides while I'm presenting. Yeah, I have to look back. I don't remember. But it was in the same 10% of the area. Yeah, it would touch that. Yeah. Actually, I think it was that one. I agree. Yeah, I think it was that one. Yeah. 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 Julia has a question. Oh. Yeah, there's a box over there. Kate's got a mic too.
Okay, so while that goes around, I'll ask my question.
Yeah.
So thanks for the presentation.
Thank you.
I'm gonna put my hat on a bit of shameless promotion of the chairman as for the OCP test and validation project. And my question is, what are your thoughts on the extra cognitive complexity load that this incurs when you're basically trying to reverse engineer the design out of the code and put it into some text form, right? What is the threshold that we should set so that this doesn't become overly verbose?
I love that. So let me give you a definition. I put it in a backup slide. Let me give you a verbal definition of what I'm saying testable expectation is, and see if that lands. There we go. So a concise, testable, human-readable description from which a minimal amount of source code can be directly implemented without further information. Or a simpler way of saying it, I can lock you up in a room holding you hostage and only show you that fortune cookie size description. And I can do the same with Steve, and you both will come out independently with mostly the same thing. Your variable names might be different. There might be some few implementation differences. Okay, so it is like, what did you intend for that to do? A small enough nugget. It's almost like when you get an idea in your head, I can write that in code. That's what I'm saying. It's like, oh, I can write that part of the code. I got that idea in my head. And it's also a lot like art too. It's almost like when you know it, you say, sorry, go ahead. Julie has a question.
Yes.
Yeah.
So, I mean, we already kind of sometimes have testable specifications
Yep.
in the sense that sometimes developers have put very elaborate comments on some parts of the code that are somehow supposed to help the user, the reader, understand what's going on.
Yes.
But sometimes those comments use some terminology or some phrasing that the writer thought was very understandable and the reader has difficulty interpreting. So, I mean, your answer can be no, we just hope that things will work out over time. But do you have any kind of guidelines or something like that?
Yes.
To help people figure out what is the level of detail, maybe on specific subsystems that they should provide for different comments or something?
That's going to be one of those. Yeah, that's going to be one of those things we're going to organically iterate to. I know exactly what you're saying. Sure, Gab wants to. Yeah. And we're going to have to document that, like what we're looking for and good examples of it. It's going to happen iteratively.
The answer is in the last submission that we did on for the documentation and testing of DevMem. We also have an addition to the kernel doc guideline that we proposed. Okay, that is explaining how to write the testable expectation and also the syntax to be used and the syntax not to be used. So also with examples. However, we are still discussing with with maintainers. If it is
it's an art.
Work in progress. Yeah, it's art.
I have a coworker who likes to use the term comments are floating islands of misdirection, right? And we all know why that is. And so the other part, innovative part of this is that we found a way to like tie comments to code. That's the other aspect of this. And then there's the methodology of writing a good testable expectation. It all comes together, I guess.
How those specifications are executed? How a testing system can ensure that the behavior matches?
You would say to a tester, when you assign a tester a job, please test this code. If you have well-written intentions, your testable expectations, they can just read it and say, I should be able to write a test case from that. There you go, yeah, that's right. Like if you look, we'll look at the example here, right? If you can't write a test, if you're a competent test SDET, right? And you can't write a test, then the testable expectation is written wrong.
Is it about only manual testing? Can those be checked out?
Oh, sorry, Steve. Yeah, one more. Okay, there you go. Yeah. So I should be able to take, like you can just visually see the shape there. If it's done correctly, a test engineer should be able to write an automated or some form of test for that nugget right there, and a pass-fail test. So it's got to be testable. Right.
Is it only about manual testing? Can it be used without a human in the loop?
A human? No. No. There's two ways. I mean, this is design. This is very deep, nuanced design. I mean, we're all like, if you're here, you're above average intelligence. I couldn't figure it out until I talked to the really smart guy what the code meant. An LLM is light years behind us.
That's one. about this thing. One thing, the big thing when we made this was, I don't want you to write anything about implementation.
Yes.
The focus is get away from implementation. Tell me this is what this function was extremely complex. There's a lot of magic that goes on. And I'm like, I wanted a nice description of what it was, so you could actually test it. It says, if look at the very first thing, if this is disabled, you can just read this and say, okay, put in the inputs, and it tells you what it expects to do.
So I think the key problem.
Anything that's manual is usually an order of magnitude less useful and automated, and this looks almost like a pseudocode, and the corresponding pseudocode could be checked out.
If it's pseudocode, it's done wrong. It doesn't show
post condition.
It doesn't show intellectual depth of what's actually occurring. Yeah.
But then what will ensure that the tests written from this still match the specification? Because then if you do manual translation,
I can't promise you that the test engineer who wrote the test is going to do a good job. Like, this has to shore up organically over time.
So I think the key problem that multiple people have now raised is that this is not in any way formal. It's not in any way automatable. It's not in any way testable or in an automated sense. We already have assertions for the trivial things. Like we have locked up assertions for some of the examples you had of you're called in this context. You're called in. So it is much better to do that and have a comment on those than to have this block of elaborate comments that describe the design intent, because those things already exist, are going to be tested directly today, and they are very clearly defining the design intent. This is defining a design intent. It's not testable in the sense that it's automatically testable, which is, I think, what Paul asked or what Dimitri asked and others. This seems like a lot of work to create more work for others. In that you keep on talking about the design, sorry, but you keep on talking about this will allow people to write tests after we've written this. Someone is magically going to write those tests. That's not going to happen.
It's okay if it doesn't happen. Just bear with me here. Bear with me. Okay, we took a look at a very small portion of code, and we found 2 legitimate bugs, one that can't be fixed. So there's a lot of dark corners in a very big kernel. All I'm saying is when you have specified what your intention is, then you can verify that intention.
But I get
you
that.
can choose not to verify.
I get that, but I think
I want to say, like, if this example, you're right. I think we could change if the intent is we want this to be automated. I think we could convert this to that. Now the thing is, how do we define that language to convert it so now we can automate it?
So I appreciate that, but I think there's 2 things. One is it's not automatable, and one is that this is a lot of elaborate text which is not in any way, doesn't have any sort of like formal semantic that's consistent. We have tons of comment blocks in the kernel that are utter nonsense that no one does anything with and that always go out of date. This is not going to help with that in any way, shape, or form, because it's just adding to that pile. Whereas if we have things like locked up assertions with comments associated with them, like we can do today, those things actually get tested and get updated.
So locked up is just focused on locking on specific.
Sorry, I appreciate that, but one is things like locked up, because we have they are.
But I think this is actually defining what is the design. I mean, you can't. This isn't. Every function's different.
So yeah, this is defining the design intent, but it's not testable. So there's a big difference.
This can't be testable.
It is testable.
It is testable.
It is absolutely
testable.
testable.
This is absolutely testable.
It's a matter of labor. I understand what you're saying.
KUnit will test this.
Yeah.
Well, no, KUnit won't test this. People can write KUnit tests against this.
But I'm saying
but the unit test of the
so you're saying is if we converted this to something that was then automated, so KUnit tests can testing.
I think you want to define formal properties that are actually useful for testable, like are interrupts enabled or interrupts disabled is one thing. Are we called in this context? But as soon as you get to a more elaborate semantic, like some of the things here, I don't think this is actually helping. It's just a big wall of text. No, sorry, people read the code and found a bug. I read code and find bugs all the time. I don't have to write an elaborate series of comments that no one's given ever update. Okay, I'll stop. Thanks.
I mean, in the patch set submission that we did on DevMem, when Alessandro, that is here, he wrote the K units associated with it, with the code. Basically, he found he found constraints on the usage of certain functions that were not clear. And
so I appreciate that, but I think reading code and trying to write how it works, you find bugs. I think that the write-up itself is not all that useful after the fact. That's the key thing I'm trying to say versus.
You missed a quote that was asked before there from me. that was, where was it, go back?
Yeah.
Wait, no.
Wait, no. I know what you're saying. Yeah.
Yeah, the one quote where
this is right here.
This one.
Yeah.
Because this function is the thing. You've looked at this. This is what enables trace events. And you could have it could be soft disabled. It could be triggering triggers. It could be triggered. There's a whole list of requirements that this one function implements. And every time I look at that, I get confused. And I wrote the code. So when they wrote that up, I'm like, thank you. You made a nice formal thing. This is okay. This may be, you said there's a lot of text here. This is one of the most complex functions in the ftrace code. And you know about ftrace code. It could be complex. This is one of the most complex one. That's why I told him, could you please describe this one? And I was like, thank you. So it's an over exaggeration. So there's a lot more text. This is not.
It's an unusual case.
Yeah, this is not a usual case. There's a person with a hand up. You can.
I'll go in. Well, it sounds like it's just an intermediary step to writing tests. Like the bugs you found are because you wrote tests and that verify that something is wrong. And this kind of adds a step in between. If someone has to write a block of text, and then maybe at some point someone in the future will write a test out of it, which sounds like just like an extra step.
But how do you ensure that the person writing the test is writing it from the central idea that is agreed upon by the developer? That's all I'm saying. If you don't want to go by that, you can just go off on your own and YOLO a test all you want based on your educated guess. But not a problem.
The test matches that, what the test expects, matches what the code does. And if something else happens, then the test will catch it. But now you're adding a third thing into the argument that you also have to make sure that the spec also kind of matches.
All you're doing is writing a definition that they both work from.
So what you're also doing is you're giving it a hook point to connect the code to the tests. And if the code changes or the test changes, you have a ways of starting to link this stuff together and actually inspect it to see if things. So if a bug fix happens in code, it's going to change the hash. And you might want to relook at your expectations in the tests to make sure you have to update it or not.
Why would I need to look at the expectations if I?
Because if
what if it passes and it shouldn't pass? What if no. I have written a lot of code that has passed the test that should no longer pass the test. I do that all the time. It happens all the time. The only way you would know that is if someone's alerted to, you might want to take a look at this, and that's what the check system is all about.
You might as well just write the test and catch the test.
How do you know it comes from the same central idea?
You have to write that in the spec.
Right. It has to come from the
I think
same
we're
idea.
going to be carrying a lot of this conversation off in the hall.
Yeah.
Igor has one more question, I think. And back there first.
So I'm kind of wondering based on the discussion so far. This is starting to look to me like kind of a workaround to deal with the complexity of the code itself. So wouldn't it be better to invest this time into actually simplifying the code and decoupling it more than having to write this additional description?
No matter what you do, you can get the greatest developer in the world. I can give them a task complicated enough that they can't write code. Good.
Along this exercise, Steven simplified the code. Because, right, Steve? You submitted a patch where you reworked the documented function because we found parameters that were redundant.
There's always a semantic loss.
So
when you
basically,
write code.
when he actually did basically, I told him, they said, get rid of the pseudocode, just write what the inputs and outputs are. And when we did that, I realized, oh crap, I had duplicated code. Because you're right, the function was so complex that when I actually wrote this up, I was able to redesign the function to make it simplify it and better. And I wouldn't have been able to, I never did that just by looking at the code. It was when they actually wrote it out in plain text. I went,
sure, but this is like an outcome of the exercise, right? But do you need to document the exercise?
You'll never get code that is just revealing all its assumptions. Not at this level of complexity. Thank you.
Okay, and again, thank you. I think we're at time, and we've taken up. So I think this will be a hallway conversation. Okay, and we'll switch it over for the next speaker. Thank you very much. Go for it. Who wants the microphone?
Theory.
Okay, it's working, right? Back and
Oh,
forth.
there it
Yep,
is.
you good. Okay.
Yeah, here it is.
Okay, then let me just start you guys off. Okay, and with that, I'll encourage those who are continuing on the last conversation to go out in the hall, and we will start on to the next presentation. Thank you very much.
Awesome. Cool. This one working? Hello? Good. Is this mic working? Sorry. You guys hear me? We'll just pass it off. Hello? There we go. Awesome. Yeah, so this is the last topic of the day. This is automating Linux kernel documentation for safety critical compliance through large language models. This is working out. Cool. Awesome. Yeah, my name is Grant Stensland. This is my coworker, Justin Stanley. And yeah, before we kind of get into the agenda, just kind of give a background of who we are and some acknowledgements. We're Vidovich Engineering Solutions, or VES. We're a entity of Wasabuck Defense, and which is a 100% tribally owned holding company. We got members from East Coast to West Coast in the U.S. And our core competencies are, sorry. Our specialties revolve around embedded environments, whether that's embedded hardware integration, OS development, BSPs, application porting, from general computing to embedded computers. Our main focus is developing deployable software products with a security-first approach. Kind of a just quick shout out. Thank you for the community. Thank you for hosting us and accepting our title or our presentation. Thank you, Stephen, for being the primary contact for giving us some validity feedback results from some of our artifacts that we're generating. And to the ELIZA team for spearheading this major effort and basically sparking this investigation just to see if this can help. If you guys like this topic or the one before it, there's an entire microconference tomorrow, Safety Systems with Linux microconference. And that'll be starting at 10 a.m. in Hall B4. And these are some of the topics that will be conducted. All right, agenda. So I'm going to kind of bring you through a motivation and then a case study. And then I'll pass it over to Justin just kind of for the technical breakdown of it, all the nitty gritties. And then I'll kind of go over some results that we got from this and future steps forward. And then just end with some questions and comments. Yeah, so the motivation, why to look through this? So despite its technical maturity and reliability, Linux is unusable in safety critical applications, kind of in the domains of aerospace, automation, defense. I'm talking about safety critical applications. I'm talking about flight controls, ejection seats, airbags, where you won't see 40 million plus lines of code in that system. And it's not performance, it's compliance, which standards such as ASIL and DO 178C require standardized documentation. This documentation emphasizes accuracy, reproducibility, and traceability. And producing this documentation manually is slow and costly, often taking years of effort, especially when not done up front. There's a growing gap between open source innovation and the rigor demanded by certification authorities. So what can we use potentially to help us, at least with generating comments? So large language models, they can summarize complex functions, explain algorithms, and highlight assumptions. Models can potentially detect undocumented edge cases or conditions needing clarification. Large language models can help translate expert level kernel code into safety auditor friendly language. Some healthy negatives of LLMs is they can't guarantee correctness or formal verification or certification compliance. I think the value lies in accelerating documentation and not in automating
the entire certification process. So as far as the case study that we used for this project, it's pretty simple. I mean, applying LLMs to ftrace utility. Explore whether locally deployed LLMs can automate documentation generation that aligns with safety critical standards. Yeah, use it on the ftrace utility. Some of the evaluation metrics that we were looking for was, quantitative and qualitative metrics for each LLM used. Yeah, computational performance, validity, and standards alignment, generated documentation, and reproducibility of outputs. The workstation that we were using was something simple that anybody can try and practice on. It wasn't pigeonholed by some super server with a login or anything like that. The specs were just Ubuntu 22.04 through Intel i7 processor and an NVIDIA RTX 4080 GPU, which is the equivalent of 3070 Ti. The families of LLMs evaluated were Metalllama, StarCoder, and Mistral DevStral. And I'll bring you through a little bit of just kind of the down select. Oh, there it goes. Why we chose those. Some of the qualitative metrics that we wanted were compatibility with the Ollama framework, and Justin will kind of go into that if you guys are unfamiliar. We wanted the models to be, pretty popular, mature, and stable, not some, edge case of a LLM. And for compute efficiency metrics, we wanted to be kind of similar in size, parameter count, and speeds. The way we figured that out was just kind of running a benchmark test against some in-house C functions and using the prompt on the right. And yeah, the prompt got way better over time than that, if you guys can read that. So yeah, with that, I'm going to pass off to Justin, and yeah, he'll kind of go through technical breakdown of what we did.
Yeah. All right, hey everyone, thanks for attending our talk. I'm Justin, and I'm going to be going through our architecture and design supporting this project. So starting off with the primary behaviors we wanted to see from the system. First, the conciseness of the output. We wanted the documentation being generated by these models to be as short and to the point as possible. We wanted to make them easily reviewable so that it would achieve its purpose and take some of the burden off of the maintainers whose projects this would be looking at. We wanted to minimize any ambiguity in the generated documentation. We wanted it to effectively communicate the traceable requirements, similar to what Chuck Wilbur was talking about before us. This is emphasis on assisting excuse me, the formal documentation which is required to enable these safety critical systems. The second main behavior we wanted to see was reproducibility in the outputs. We didn't want super noisy outputs from these models. And this supports more reliable testing, and it helped us more effectively iterate over our prompts and find what worked the best. We didn't want small changes in our prompts or small changes in the configuration to dramatically affect the output. And this also ties into iteratively improving the system. The third behavior that we wanted was robustness in our model backend. We wanted to easily deploy the LLMs to target hardware, regardless of whether it was locally or an on-premise solution. We wanted the inference from the models to be remote so that we could decouple the comment generation process from the machine that required GPUs to run these models. And finally, we wanted a modular deployment so that we could easily interchange these models, compare them, and see what produced the strongest results. Oops. Okay, so doing this documentation is a monumental task. The Linux source code is massive, and we made use of multiple open source suites to help build a system that could do this. So first one we used was Ollama. This was our open source LLM backend. It supported remote inference via a REST API, and Ollama also had a public model registry, which allowed us to easily pull down different models from the web and compare them. It also supports multiple models locally, which further assists in comparing them as quickly as possible so that we can narrow down which one's going to be best. The other open source software we used was TreeSitter, which is an open source incremental language parser. It is language agnostic, so it supports multiple languages. And for our project, it provided a reliable parser so that we could take source code and convert it to syntax trees, which we later used to help validate our output and reconstruct our output into patch files. And we'll go into that later. So first, let's talk a little bit more about TreeSitter and ASTs, what they are, and how we use them. So TreeSitter is an open source language agnostic parser. We are focused on parsing C code so that we can target the Linux kernel. If down the road we wanted to consider documenting other projects in other languages, the only thing we would need to do is find a new parser module, because all that we need is the AST. And the AST is an abstract syntax tree. For those of you who don't already know what it is, an AST is an internal representation describing a program's semantic meaning. And it's used by compilers for generating code. It really is, it's an abstract data structure which describes how the program works, how it is put together syntactically. We use them to pull out functions which we are trying to generate requirements for. We also later use it for building and verifying the newly generated source files. So on the left here, we can see an example of what a basic AST might look like. So for the source code above, very simple C code, we have one global variable, which is a child of the program. The second child of the program is a function, and all of the children of that function in the AST are the components of the function. So we have, starting off with the local variable, then a comment, and then a statement. And this is a very basic AST. One that's actually used by a modern compiler like GCC will look very different. For instance, the statement won't just be text containing the statement. It'll be its own parent node with children for each parameter, and those parameters will have children referencing the variables. For our project, though, we're mainly just concerned with the functions. So let's also briefly go over OLLAMA. So OLLAMA, it's our LLM backend. It supports a wide range of target hardware for both local and on-premise deployment. It's GPU agnostic, so it can leverage hardware acceleration on NVIDIA platforms via CUDA, AMD platforms via ROCm, and if you don't have a GPU, then a CPU, it can leverage with AVX. It supports remote inference via REST API, which also enables easy load balancing, and has a nice suite of mature client libraries for Python, JavaScript, and Go. For our project, we use the Python API. And as mentioned before, it has a public model registry, which we use to easily interchange models. So let's go into the pipeline. So our pipeline translates input files into a collection of patch files for quick review. It is parallel, so it can be run concurrently per input file. As it uses OLLAMA, it has a swappable and load balance backend. And we implement two different kinds of verification. We have an implicit verification layer and an explicit verification layer. And when I say verification, what I mean is, so the top priority of our project is to help maintain safety certification for this code. So we do not want to affect the code behaviorally or functionally at all. We only are interested in generating documentation. So we verify that the code does not affect, that our patches do not affect the behavior of this code. So implicitly, we verify the code semantically, and this happens before patch generation. We also have a layer verifying the code explicitly on a kernel built from this patched code. Finally, the output from our pipeline is a collection of patch files which are ready for review or as a starting point for later refining documentation. So let's talk about the first stage in our input pipeline, the function parsing stage. This is the initial stage responsible for extracting the structured information from the source code. So we take the source code, immediately pass it to a parser, which uses TreeSitter to extract all of the functions from the top level scope. We're interested particularly in the function body, so the source code of the function, the function signature, including the parameters and the return value, and also the function's location, so the file which we found it in and the line number which it was defined on. We take these parsed functions, hold on to all of the data, and pass them to the next stage, the input chunking. So the input chunking Now that we've collected all of these functions from the original source, we get ready to submit them to the LLM. However, LLMs have input size limitations. If functions are too large, then we need to split the body into multiple chunks. But how do we pick those chunk boundaries? If we just take the function source code and pass it to an LLM, the LLM will chunk it, often via something we call naive chunking, where chunks are aligned exactly with the LLM's token limit. But LLMs work with different languages than compilers. A token in C might get cut into multiple tokens through the LLM if we just directly send it over. So what we do is we perform smart chunking. We take the source code, we pass it to tree sitter again to identify the boundaries of the C tokens, and then pick a spot between the C tokens such that we don't end up splitting that into the LLM inputs. Because if the LLMs receive a token from C that's split into multiple pieces, it's going to harm the quality of the output. It might start hallucinating. It might produce bad documentation. So we use this smart chunking to break the code into ingestible and independent chunks for the LLM. Now we move on to the comment generation stage. So we have these functions with metadata and chunks appropriately picked for an LLM. We send them now to OLLAMA so that it can produce the documentation we're looking for. So we use a fixed prompt with instructions, which we'll discuss in a moment. We combine those with the source code. We hand them off to OLLAMA and generate the documentation. We receive that and save it along with the function data. And then we will pass that to our next stage, the input recombination. But before we talk about that, let's talk about the prompt selection. So we have a fixed prompt to instruct the LLM to generate the documentation, but how do we pick the right prompt? So what we did was tried to follow some established formatting from existing ELIZA efforts with an emphasis on producing traceable requirements like Chuck was talking about before. On the top right, we have an excerpt from a patch on the ELIZA GitHub, one of the Linux forks. And this is, you can see, it has the SPDX tags, although these are currently placeholders, but it also has documentation for each parameter, and it has the bulleted lists of function expectations. And we tried to match this format as closely as possible. However, we left out the SPDX parts for now because these are not ideal candidates for an LM to generate. These are unique IDs, which need to be unique, and they need to reference each other and build this formal structure. And LMs are probabilistic. This is not something they're strong at. So this has been moved to the future work for this project, where we use the LLMs to focus on the function expectations and the descriptions of the parameters, but we will later ideally add SPDX tag generation directly and merge that with the LLMs. So after iteratively refining the prompt, we found this one shown on the bottom right, which produced the most consistently formatted output in line with the existing efforts from ELIZA. And now that we have these functions with documentation generated from our OLLAMA instance, we move on to the input recombination. So the common generator produces a collection of these functions with metadata, the function's body, and now this safety compliant documentation. But we don't have a complete source file yet. We just have all of these functions. So we need to reassemble it into a new file so that we can produce a patch. So can we just concatenate everything together? No, there's a whole bunch of code that we didn't really look at. There could be macros in the files, comments at the top level. So we need to reassemble the output by being aware of the original source. And we do this by leveraging tree sitter. So some function metadata that we stored earlier, we are especially focused on the location. We use the file name and the line numbers from where we originally found these functions to know where to insert this new documentation which we've created. So following this process for every function, we insert the comments we've generated and construct a complete output file. And now we have a complete output file. We're almost ready for a patch. But now this is where we perform our implicit verification. So how do we check? We have a new source file and an old source file. We need to make sure like only comments have changed. We don't want to touch any functional code. So we reparse the new file, reparse the old file, and compare the ASTs to verify that nothing's changed. Because in these ASTs, all of the non-comment nodes are the functional nodes. So if we take the ASTs, trim out all of the comment nodes, and they're identical, we know that no behavior has changed. And this is exactly what we do. So to verify, here's an example of some two ASTs which we might compare to perform this check. So on the left is an AST that we might see after parsing some undocumented source code. And we see it's only behavioral components. We have global variables, we have functions, variables, and statements. And on the right is an AST we might parse after generating documentation for this program. And we see if we trim out the comment node, the ASTs are identical. And this is how we verify and guarantee that the code has not been functionally changed. And at this point, we have a complete output source file and an original file. We can use the Unix utilities like patch to generate a patch file and have it ready for review. We also have an optional stage, which we implemented in our system. We deployed the pipeline into a Jenkins instance to support development and improve the validation. And this helped us more rapidly iterate on the project, test what we had, and find what worked the best. So what we did is created a pipeline with inputs containing the source files, Git information, the LTP version. It would generate all of these patch files, apply them to the kernel source. It would build a kernel artifact, start up a VM, and then run an established test suite. And for this, we picked the Linux test project because we could run tests specifically on the subsystems that we modified. And this added another layer of verification so that we could check at runtime that the system was still behaving as it should according to this test suite. And with that, I will, that covers our pipeline architecture. I'll go ahead and hand it back to Grant.
Cool. Thanks, Justin. Yeah, so just some results from our findings. You can kind of see just the original undocumented source from ftrace. And halfway through the pipeline, it creates just a actual file with literally just a comment block on the top with each and every function as broken out from the AST. I don't even know if you guys can read that from there, but there's no like metadata or anything. This is strictly just comment generation right now. This project's very early on in its life cycle. So just test results continued. Yeah, so eventually you take all these separate functions with comments on the top and then throw them back into an actual, back into the file and then create a patch out of it. And that will be a resulting patch. That's kind of the artifact that you get and what we'll send to Steven or whichever maintainer we're talking to or who we're in contact with at the time. More results, just kind of model comparison. There was from the 3 DevStral Star Coder 2 and Llama 3.2. There's not really any strong link between metrics and documentation quality. And everything's pretty linear, like CPU, GPU usage, time to completion, basically is linear with valid responses. But we did kind of notice that from where our project was at the time, our metrics, DevStral actually proved to be the most valid response giving large language model, which was, I'm sorry.
No, it's okay. I just wanted to ask a question. I was just wondering whether or not you looked at any code coverage metrics, like for how much your testing is actually covering the code, and are you increasing the amount of code coverage with this methodology?
Good question.
Okay. I'm just thinking that might be a way of basically proving out that if you extended this up, you're going to hit more of the code and you can prove it out.
Yeah, definitely. So this project was focused on generating documentation.
Yeah, I know.
Yeah, but like Chuck was mentioning before, a lot of these requirements will map directly to test cases. So what we might be able to do is either manually or down the road, possibly even automating the generation of these tests, we could see how effective these requirements are at properly covering, at achieving the code coverage that a strong test case would.
Okay, I started them off.
All right. Yeah. So here comes the dominoes.
How do you verify that the added comments are actually what the code does. So it actually are correct.
Right.
So a lot of the so the idea is not to replace someone who's writing these test cases, but rather to help take some of the work off, because a lot of these functions, there may be a huge number of these methods, or the methods may be very long. The idea is that these would be reviewed by the expert, ideally who wrote them, but someone who is familiar with the function. This would be a major time saver.
Okay, yeah, so you still need to collect that, I guess, data. I'm not sure if the plan is to send this, I mean, the output of your running your model, and that which has the comments, send it out upstream, and then listen, see how over time, how much of those were, I don't know, rejected, accepted, and build the that data with time. I guess that might be one way to assess how good this is. Okay, yeah.
Definitely.
Makes sense. Yeah, so just last section is just kind of next steps, what's in our scope, and where we can go forward with this. Current limitations, model limitations. There's always an inconsistent mapping between natural language and kernel level code. That's just further prompt refinement, and that will continue as long as this project keeps continuing. Technical gaps, requirements to code traceability not fully automated end to end. As far as like metadata and traceability and all of that, that's in the future. So at some point, it'd be nice to have actually SPDX tags added. And then there's also the operational constraint, which is it's heavy on subject matter experts. We don't really have an in-house way of testing validation or validity for the comments generated. So it's kind of like a cycle of sending it to the SME and then receiving it, further enhancing the prompt and everything. As far as next steps, yeah, pretty much what I just said. Prompt refinement, ongoing collaboration with maintainers, SPDX-driven requirement tracing. This is all things that have to continue forward to make any progress with this.
I'll just point out that the patches for the functional safety profile or system engineering, it's being debated what it's going to be called at this point, are actually starting to go in upstream right now, and they'll be the basis for whatever tags tag for evidence. But what's there is being prototyping.
Cool.
Okay, and so things will refine themselves.
Cool. Yeah, that's awesome. Yeah, so I mean, that's pretty much where our next steps are leading us. 2 GitHub repos we have public right now are Llama Co-op DocGen and Llama Co-op Jenkins. They're open to any kind of contributors of any level. DocGen is just the Python scripts for automating code documentation using the large language models. And then Jenkins is the pipeline script used to automate build, test, and deployment processes. And the URL's right there. Yeah, I think that's it. Any questions?
Chuck it at me. Are you guys doing any tools qualification for this?
Sorry, say again?
Are you guys doing any tool qualification for this?
Tool qualification?
Yes. The LLMs, you mentioned you're managing chunking to reduce hallucinations, but how do you know it's actually not hallucinating?
So we're trying to minimize the hallucinations by making the input as sane as possible for the LLM. But the intent is not to remove human review. So
yeah, so
will need to,
at the end of the day, you're relying on maintainers for verification of the output.
For the final check, yes. This is ideally going to save a lot of writing time, but still, it's not something to be like relied on, especially for a safety critical application. This is to help close the gap, remove some burden from the maintainers.
I mean, there's work on both sides. There's going to be a trade-off of work trying to get the prompt and actually the large language models to work correctly. But in the end, I think overall it could, help
Okay.
Did you work on the same function that was mentioned in the previous?
No, I believe it was a different method. This was a shorter method. The other one was significantly longer.
Okay. And another thing is like when you work on different functions in the same module, for example, do the comments come into the same mental model? Like the level of abstraction consistent?
When you say level of abstraction, are you referring to like whether the requirements are in alignment with the original design intent?
No, it's more like you have some kind of, I mean, you start out staring at the code, and that would be a very low level of abstraction. First we do if X or something like that, then do something, no one is going to gain any understanding from that. But after a while, you might have a higher level of abstraction, like test if X is even number. You might realize that even numbers are very important in this context for some reason. So then you might like to write the document or generate documentation for all of your functions in terms of whether numbers are even and odd, and not in terms of dividing numbers by 2. Or, I mean, it's a silly example, but I'm just trying to illustrate that. But I wonder if you would get the even odd consistently, or if sometimes you would end up with division by 2, and sometimes you'd get even and odd.
Yeah. So that's something that
You're saying, are you getting coherence in the comments?
Yeah, definitely. So that's something we try to address with the reproducibility behavior. So we want a prompt that is going to effectively guide the LLM to consistently make that decision to simplify that even or odd pseudocode into the same language. And that's something that is a matter, I think, that can be addressed via prompt refinement.
Any other questions? Okay, well, I think we're at the end of the day, so please thank our speakers. And the referee track will resume tomorrow morning at 10 a.m. Thank you.
You guys are free to go.
And yes, and instructions on how to get to the event are on the back of your badge. I want to go and take a look at another. Yeah. That's what everybody wants to
This is the safety architecture. This is another one. Oh, Zephyr. Okay, I see.
So it's a completely different code base.
Okay.
But it's a kernel. It's an argument.
Okay.
And we're going and we're going to 61.5 right. Actually got tons of kernel. We have the code part of the test linkage there. We'll be able to certify it. probably for the end of the year, I don't think I'm meeting or not next week. But yeah. Here. Thank you. Thank you. Thank you. Thank you for coming.
You guys know where the evening event is?
What?
You should still go to it. You know where the evening event is? You can look at where it is, the address?
Yeah, it's quite a walk, but I'm gonna walk back to the hotel and go sleep myself.
It's next to our hotel.
Is it really?
Yes. Which hotel? Sheba Park. I mean, put it this way.
Okay.
I went down, it's like, here's our hotel, here's the event.
Yeah, yeah.
We walked past it on the way here. I'm like, you guys are going to the event, it's right next to me, come on, it's next to the frickin' hotel. That's our, no, that's the. When I'm in the event, it counts as I'm at the event. Okay. So, just be, well, I'll see you guys later. See you guys later. I'm about to run off. What? I'm about to run off, what can you do soon?
We need to update the registration method for ACC message. We're going to expect everyone to don't know where to log in because they're now they get mail up, right? And they're also they have to.
That's what talk to James. James is the one who controls of the.
I'm not sure if it is James or through.
Mike, I think does the conversion, James is the email guy.
Okay, so I think Jason messages registration.
Yeah, oh.
Who does that?
Oh, registration.
Yeah, it's registration.
You are currently the only person in this conference.